Indeed. Okay, awesome. I think we're actually rolling nice. Good after. Sorry. Yes, I'm assuming you can hear me. Tell me if you or wait.
Good afternoon, Professor, and yes, I can hear you.
Okay, awesome. Thank you, Juanita, very much. And thank you, Shankia, for being number one. Good afternoon, Shankia. Good afternoon, Hoyin. This is so satisfying. It's like, I really feel like even in this moment, I'm getting, anyway, whatever. I'm so glad you guys do the hellos. I think it makes a huge difference. And these little check-ins every day, I feel like I know you people, which is crazy because I totally do not. But okay, good afternoon, Shankia. Good afternoon, Hoyin. Oh, wait, someone else is coming, sorry. Wait, where'd they go? Where'd that person go? Wait, sorry. Someone's trying to come in. I'll do the hellos again. Why do I never do this right? Okay. Good afternoon, Shankia. Good afternoon, Hoyin. Good, another. You're doing this on purpose. Okay. Good afternoon, Jitlali. Good afternoon, Catherine. Good afternoon, David. Good afternoon, Renice. Good afternoon, Tomika. Yes, oh, yes, thank you, Jitlali. Got it, right. Good afternoon, Jacob. Oh, that's so nice. What a nice, I'm not even going to read that out loud, but thank you, direct chat person. That is, and there's only one of you at the moment, so you know who you are. So thank you. That is a nice thing to say. Okay. And helpful for future Zoom years. Okay, good afternoon, Aja. Oh, and more people are coming. Excuse me. Okay. And then all people coming. And I'll say this too, in all seriousness, I do feel like, I think it is fair to say that many of you, even if you think you're sort of a quiet person or whatever, just between these like hellos and the game turn things, just between that alone, I will say that I feel like I know a great deal of you, or most of you, better than I've often known people back in the day in non-Zoom classes. Like there's many reasons for that perhaps, but maybe we all have to try harder here, but like for reals, and I should quickly, oh, good afternoon, Edie, thank you. And good afternoon, Aja. And wait, we're about to be, hold on one second. No, yes? Okay. And even though I've been a little flaky sometimes about it, I will say too quickly, since this is 204 and I won't see you again after this, when the whole class is over next week, if any, whatever recommendations some of you might be pursuing either right away or later in life, either for something as simple as the MSRC or being a lab tech. Oh, in fact, very specifically, if any of you just want to be a lab tech next semester, you should maybe reach out to me privately, like by text. And because I am supposed to submit names for that. But anyway, if there's anything you're looking for, like that, or like graduate school or graduate programs that could be later, I do feel good about this class so far. Obviously, I still don't have your exam scores yet, so I suppose that matters. But do feel free to reach out through email and stuff, and know that I do know how to write a Zoom-based recommendation at this point, if that makes any sense. I think there's a whole new style for that, but it exists. But anyway, all right, okay. We're going to get rolling. We have a lot more to do. I don't have the exam scores yet. Hopefully warn you of that, but you will have them one way or another before Monday, and then we'll talk about that Monday. And of course, we'll have then 3 fast days to talk about the final. We'll get to that. Oh, great. Okay, wait, sorry. So and I didn't mean to get back. Yes, so thank you. All right, 2 different things in the direct chat. How can I address? These are actually like vaguely private. So yes, just that's awesome. You in the direct chat who's asking something about your life, like, yes, I agree. And yes, I would be delighted. And just remind me or reach out to me in a text or an email, and we'll work it out. We'll happy to. But then also there's something in the direct chat. Yeah, about the you subscribe. I don't think I messed this up. Maybe I did, but there is a portal. So this is an answer to a direct chat question. There is a portal called You Subscribe, which is for a game turn portal, which you can submit at any time, even next week, where you get points for sort of any attention you paid toward YouTube's at all, or any use you made of YouTube's. The easiest possible way to get the points is just subscribe to the channel. And then you could screenshot that or whatever, but you don't even have to, because actually, as it turns out, if you subscribe, then I find that out. So I know it. So even though I know it, still to give you the points so that you can actually get the points, I just need you to jot that fact down. Like if you subscribe to the YouTube channel, and it's still totally not too late. In fact, it might be particularly important before the final exam. Just jot down on a document, just open up a document in that portal and just say like, I subscribed, remember? You don't have to subscribe, because I'm not trying to make this like a marketing technique. If you just have any way to remind me or tell me that you actually like made use of or showed interest in any of the YouTube videos at all, just tell me that in the You Subscribe portal, and just like a normal game turn portal, and then you'll get the points for it. But sometimes there are those of you that I'm reaching out saying, hey, I noticed you subscribed. Please put that in the portal. And you might be thinking like, well, if you notice that, just, give me the freaking points. Yeah, I'm like, why do I have to? Well, there's a couple of reasons for that, but the most basic reason is I can't give you the points, like, unless it's through some assignment. Like I can't, because, all points are in Google Classroom associated with assignments. So all you got to do is just open up that portal and type a quick thing into a document, and then there you go. Am I answering the question? So I hope like that answers the question, and it's still not too late to do that. Also, quick on the YouTube thing, you may have noticed, I'm really bummed about what I'm about to tell you. I'm sure I'm more bummed about this than you guys, but the lecture from Monday, which was a kind of an important lecture, I'm going to make some references to it today, and it was meant to be super helpful for your lab work. And it was a dense lecture, but or the class, whatever, Monday's class, the entire recording got botched. It took me 2 days. I couldn't understand why it was taking so long to upload. I still don't totally understand what happened, but somehow the whole thing got recorded on some super fast speed or super slow speed or something, so that the whole recording ended up being a 24-hour document itself. And believe me, I tried to edit it down, but there's just something messed up at the root. Okay, I'm going to look. Okay, I'm going to look. I see these things in the direct. There's a good question in direct chat. Okay, I may even pause to answer these. I see the questions in the direct chat, but just anyway, on YouTube, Monday's lecture just got totally botched, or the recording of it did. And again, it bums me out as much as you, because I would have used it for future classes, but it got botched. It is at least irretrievable to my technological level of skill. I did try a number of things, believe me, but so it's gone forever. So that's why the lecture, if you're ever trying to review for the final or anything else, the YouTube lectures go like class number 7, class number 8, class number 9A, class number 9B, and then 10, which is meant to signify there is no actual recording of class 9. There is a PDF of all the notes, and I please do, and that's in the Google Classroom. Please use that. Like, the material does exist. You are responsible for it. We did have a class on it, but there's no recording of it. However, recordings 9 and A, I highly recommend like looking at. They're different. They're very, very related, but they're sort of better in different ways. I might open up a portal just for bonus points, just for looking at those. They will help you with the material that we're about to do. They're not the same, but anyway. So that's the best I got, is that they're not the same material that we did that day, but they are important material to help us move along. So the YouTube lectures go 8, 9A, 9B, then 10. That's it with that. I'm going to go back to that material in a moment. But yeah, there's a question. All right. There, and hopefully maybe you'll tell me, direct chat person, if I did answer your You Subscribe question, because I feel like maybe I didn't. But okay, there's a question in the chat I have to think about for a minute, because it's definitely important. Okay, great. Thank you. Thank you. Okay, question in direct chat. Yeah. Okay. I'm going to read out the question. It's important, and I'm not. Oh, and there's someone here. I'm not frustrated by it. I have to. It does raise a complicated point. The question in the direct chat is, how's the final going to work, and the due date for it? Because Wu said he's trying to assign a due date for the post lab and the formal 5 that won't overwhelm us. I'm very glad to hear that Wu said that. I totally appreciate that concern. I do know that you guys got overwhelmed by being hit so hard with the labs and the midterm last time. We do try to avoid that. I mean, at some level, it's just the nature of a crazy 5-week course, which is crazy. I mean, some of this is unavoidable, but and slight stall on this question. I will say, For this, you'll know, I didn't post any new homework yet. I mean, there's homework due today, technically, and I saw like half of you turned it in. Thank you very much. We're gonna keep talking about it today. At least as of right now, 5 days, I'm not going to assign like a homework 6, which I was going to. I'm just going to say you have catch up time on homework 5 if you haven't done it. If you have done it, but you learned things today that help you with it, you can go back and redo it. Some of you never handed in the end of homework 2, and that's because I kept saying, we'll get to this later. This is an opportunity. If you never got all the points for homework 2, I would say use this weekend to do that, because everything we're about to finish today and those 2 YouTube lectures I posted, 9A and 9B, those will together, like you totally can do homework 2 if at the very worst you watch at least one of the YouTube lectures I posted, at the very worst. Plus, I think that between what we did yesterday and what we do today, you'll be able to do it. But so basically this weekend, even though it's a very long weekend and it's kind of like the last weekend, at least right now I'm saying it's basically catch-up time for all of you. And hopefully time for you to catch up with like lots of overwhelming lab stuff. That still does not answer the question, but it's a little bit of a gesture of compassion. Because yeah, next week is going to be crazy. So what are we going to do? All right, I want to get rolling, but the direct about the final, the thing I need to know, I'm going to look up right now. The thing that drives everything is when are these grades due? So pardon me for a second. Okay, I'm going to ask you all 2 questions. One, my understanding is our very last class. Yeah, I think someone confirmed this yesterday. Our very last class is a week from today, Wednesday, the 18th. And I don't believe there's an extra final exam period during the summer. But the question is, when are my grades due? So hold on 1 second, please. Unless you happen to know, I don't really know why you would. Oh, okay. Okay. So the last day to submit grades is August 23. I apologize for the delay, but this is definitely a important question. Okay. Oh my God. Okay. Pardon me. What? Just bear with me for a second. Okay. So your class is in. Yeah. All right. Well, this is going to be tight. I'm going to put this in the chat right now. I mean, this is a very important question, and you're not going to love my answer. It's the best answer I can give, all things considered. So I'm going to put my answer in the chat. Obviously, I'll post it in Google Classroom too. Oh, wait. Oh, yeah, that's fine. And anybody, look, with homeworks, you still have, telling you all, you can still hand in any revision or any amount of homework or whatever, all the way up until next Wednesday. That's not an issue, and without penalty. Again, I'm sort of rigid about aspects about the exams being on time or late, and people have been very good about communicating about that. With the homeworks, you don't even have to apologize or whatever. The homeworks, you just, get them in by the end. But as far as this question about the final, I'm going to put in the chat right now. I might even put in Google Classroom right now. Today's. Okay. Oh, I should. I'm gonna, what I just put in the chat, I'm gonna put this in the Google Classroom right now also. Again, I know that, and this is kind of not negotiable. Okay, this is a very good question that someone just put in the private chat. It's totally fair. It's more than fair. Like, you obviously need to know. Unfortunately, things are so tight that I'm telling you now because you need to know, and I'm glad someone asked. This is not something we can really discuss. This is the best thing I can do about this, which is why I'm going to just try to make it as clear as possible right now in the chat and in Google Classroom. So bear with me for a moment. And it's going to go faster than the midterm. Like, well, all right, I'll explain that in a second. Hold on. Bear with me again. I'm sorry. Okay, so everybody, I mean, my job, oh, all right, I'm gonna look in the chat. I'm almost afraid to look in the chat. I'll look in a second. Let me just say this. My job is still to get back to you the midterms as fast as I can this weekend and to show you how to improve what you did there onto the final, like to alert any of you if there's any issue, if you should be worried about your grade or if you should be worried about like how you're doing things. So far, by the way, I don't think anybody's too concerned. And again, I can say so far, like there's a good chance if you've been seeing on the homework that you get what I'm asking, you just do everything that you're supposed to do and you do it on time. If you did that with the midterm, hopefully it went well for you. We'll find out. And then hopefully the same thing will happen with the final. You also will get advanced preparation for the final. Like you'll know what's on the final before it's posted, just like with the midterm. But we had to go fast with the midterm. We're going to have to go even faster with the final in terms of how much I can really like hold your hand before it. We won't be able to sit and like walk through a whole practice, et cetera, but you'll have one. And again, I'm quickly trying to say this sort of intentionally before I look in the chat. If I don't sound happy right now, it's because I'm not unhappy with the question. I'm just no more happy with how fast this has to go than you guys are. I don't like doing school this way. Okay, I really don't. But you know, it's a reality of the 5-week summer course. And let me say, before I look in the chat, the announcement, and maybe I made a mistake. And that's also, if I look in the chat and I find out I just made a mistake somewhere, you know, I'll correct it. But there's not a lot of room to negotiate or wiggle because, just to be clear, I have to get your grades in to CUNY first by that Monday. I have to have graded all your finals and then incorporated them into larger grades. Even if I didn't have a life or anything else, like that's a rather, you know, big challenge. And I know from experience, I cannot be late with your grades. I won't be, I can't be. I mean, I tried it once before, believe me. It's, so you'll get your grades on CUNY first when you're supposed to. And if I run into some major jam in it, well, we'll talk about all that then. But anyway, I have to turn your grades around. So, and technically the course is supposed to be over by Wednesday or Thursday of next week. Like we don't even have an extra final exam period the way we do during the fall or something like that. So the best I can say is I'm saying, we'll talk about the final Tuesday and Wednesday. Then Wednesday night, no later than 7, I'll post it. You will have already you'll know by then what's going to be on it, believe me, but I'll post the official thing Wednesday night, 7 p.m. And then you'll have till Saturday noon to turn it around. That's a compromise. I mean, that I can't make it any long, like that's already longer than technically I'm allowed. I mean, technically the semester should be over by then, but you can turn it until Saturday noon. The reason I'm not giving you the whole weekend or something like that is I literally can't, because I have to take them and grade them to give you grades by the end of the weekend. So I'm just kind of splitting the difference with all of you and saying you can have till Saturday noon from Wednesday night to Saturday noon to do this thing. And then I have from Saturday noon through Sunday night to grade them and turn them around. I won't even tell you what I'm also attempting to do in the background of my life while that's happening. But that's the deal. And I'm saying last thing, and again, I know I sound defensive about this, and I apologize. I am defensive because I'm like already worried that this is not a lot of time for you guys, and it may be intimidating to you. And I totally respect that. It totally intimidates me. I think it's the reality. So one other thing I'm going to say is, believe me, I'm going to figure out a way to make the final shorter than the midterm, both for your sake and for mine. It will be the same type of thing, like problems that you have to work through with multi-parts. You'll probably have a choice here or there, and the problems you'll have advanced warning of what they are. You might even have solutions to some of them, just like the midterm. It's like that, but different material. But yes, I will post it Wednesday night. You'll have till Saturday noon to do it. Hopefully that information at least helps you clarify your calendars. Hopefully you can bring that information to Professor Wu if he wants to work around that. If he wants to privately talk to me and ask me to work around a little better, I'll try. But I'm the one that has to get the grades in to CUNY first, not him. So okay, that's my answer for the moment. First thing to ask yourself, I'm so afraid to look in the chat right now, but I'm about to look in the chat. We'll address this for a couple of minutes because it certainly is that important. Again, if I sound frustrated, it is not with the nature of the question. It's with the nature of the answer. It is worth our time for a couple minutes to get this straight. The first thing I want everybody to ask themselves, though, before they start writing anything more in the chat or something, is first just ask yourself if what I'm saying is clear. Like, forget about whether you like it or not. First, just make sure you understand what I'm saying, because God forbid you can't talk me out of it, or God forbid it is the reality, then we don't want that to sneak up on and surprise anybody. So like as of right now, hopefully what I just put in the chat and what I put in Google Classroom, like maybe someone can confirm that they saw it, is the deal, the contract. All right, now I'm gonna look in the chat and see what's going on there. Oh, wow. Oh my God. Wait, I love you guys. Are you kidding me? Sorry. I wish like the government worked like this. You're like, I just glanced, but I'm like seeing, okay, sounds good. Okay, good. Thank you, Professor. Is wow. And even it's clear, got it. Good. I love you guys. Are you kidding me? Okay, thank you. Now, oh, okay. And I'm even going to say, since there's, thank you for going, it's such a nice thing too, that you guys ask your tricky questions in private, but then you give like your affirmations in public. That's really very spiritually wonderful. And I will even say that the person that asked the tricky question was one of the people that publicly said, okay, it's clear, which I appreciate. That totally counts as a bringing things full circle. Now, there are still a couple of tricky questions in the private chat. Oh, okay. Oh, wait, okay. One thing though, there's at least one thing in the private chat where someone has the honesty to say, like he understands or she understands it's non-negotiable and fair, but it's very inconvenient for that person and that person doesn't know what to do. I do want to say that, and that there's a couple people like, this is the same thing with the midterm. Look, and this is, maybe I overuse the word spiritual, but no, any of you, all of you who have specific issues. For example, like I know for a fact that the person that just wrote in the private chat that they have like a specific problem, that this doesn't work for them, even though they get that it's like fair and non-negotiable for the group. They even already warned me that they had a specific problem like 2 days ago. I want to acknowledge that here and now. Like at least one of you has already had the presence of mind, even before I said all of this, to say, there's a problem in my life that is going to conflict with the final. Look, all of you, I believe in working out individual circumstances, like as individual circumstances, especially when people communicate in advance and honestly and like patiently with me. So anything I'm saying is the group arrangement. If you have a specific, and we all know that everybody's life is specifically hard in different ways, but we also just know intuitively sometimes we have specific individual circumstances that are really actually unusual and transcend the norm. That happened with a couple of people in the midterm. That is okay. Like if you communicate with me on an individual level, we on an individual level will figure out what we can do as individuals. I can't like I might have barriers as well or constraints. We might have to, compromise or something. But no, this is always true. I mean, it's always true for me. Any one of you, I'm talking about what's true for the group. Then if you in your heart know that there's a reason that you don't fit in the group, in that case, you can come to me individually. Especially, this is a second course. This is Physics 204. There are some of you who I've had for 2 semesters, which just means this, which means I know the difference between someone who every single time has an individual circumstance or every single time is late without explanation or something. Like people build up patterns. And even in 1 semester, people build up patterns. If we're now hitting the final, if you totally sucked up the midterm and you did everything you're supposed to do and treated yourself like everybody else in the group, but you have a specific deal with the final, that you have the sort of guts or the presence of mind to communicate with me individually, we as individuals will try to work it out. That is what I believe. I mean, I want you all, and some of you, I don't want to drag this out, but I feel strongly about this in life, especially when you can see my frustration. Like, I think this is a hard task to do this final and to grade this final. I also think that's why a lot of compassion will be built into the grading and into the writing of it. Believe me, again, that's why part of the whole tone of this class is if you just stay with me and try and be honest and authentic, it's easier to get an A than you might think. It's not a joke to get an A, and it's partly easier to get an A because some people will always find a way to get an F and a D, and they will, and because blah, 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 blah. But we're not asking anybody to be like Newton in order to get an A. I'm not Newton. I have no right to expect you to be Newton or Galileo or Einstein. I have no right to say you can only get an A if you know as much physics as Newton. I don't know as much physics as Newton. This is not grades based on what level of Nobel Prize winning physicist you are. This is grades based on what level of physics student are you? Like, how well did you work in the physics class? So a lot of you should, as long as you keep doing what you're doing, you should do well. And you should understand that. And you should know that if you have an individual problem with one of these arrangements, you come to me as an individual. And some people did on the midterm, and some people, in fact, okay, let me say this. Sorry, just like school's hard. We don't have to make it harder. And physics is hard. We're not here to make it harder. We're here to make it easier. Mother Nature already made it hard for us. And when I say we're here to make it easier, I don't mean as a joke. I don't mean I'm here as an act of charity to let you out of science. I'm here to be a conduit between the complexities of nature and the curiosity of your mind. That's what learning science is supposed to be. It's like learning how to figure out how to command this untamable beast called nature, right? So we're here to try to have a chance, to have a hope. Okay, I have to make policy arrangements that will give us all the best hope across the board, such as giving you till noon to turn in your exam. If you have an individual thing, you can write me. And some of you did on the midterm, and some of you were, I think, a little confused about this or something, or were like, you would reach an individual problem and you'd say, sort of like, can we all change the midterm and make it due like Thursday instead? Because I'm having an individual problem. And I understood what some of you were thinking. I think you were thinking, oh crap, I'm having a major individual problem, but I can't like ask him for compassion on that without it being unfair to everybody else. So I better ask for the whole thing to be changed. I get that. That's like very generous of you, but it actually in my world doesn't work that way. In my world, at a certain point, we have to have a group policy that's pretty good for everybody and that's clear and doesn't change every 5 minutes. Like we have to have an expectation that people aren't confused about. But sometimes individual people can have individual circumstances. And if I accommodate those individual circumstances, and I'm insisting on this like to all of you as a human being or to the YouTube or whatever, well, I want you to know about my opinion. My opinion is that I can hear individual circumstances and accommodate individual circumstances if they're made on an individual authentic basis, like not every single time, blah, 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 but like I'm a person of integrity. I've been trying to do everything and like carry the water of this class like everybody else. But here I just hit a wall in my life. Is there any way you can recognize the wall that is in my personal life right now? If I say yes to that person, it is not unfair. This is my belief. It's not unfair to anybody else because everybody else also has that opportunity to come to me and say, I've hit this wall in my life. What would be unfair is if I just did it for people I like and not for people I don't like or something like that. Or what would be unfair is if certain people could just like not turn in the midterm, period, and like I didn't do anything about it and still gave them an A. What I'm saying is that sorry, I sound like I'm yelling, but I just want you to know there's a difference between sameness and fairness. The fairness is, and I'm also, because I'm concerned about, like, I actually know there's one person in this class who, at least one, who literally does have an issue with the final schedule, but has let me know about this days ago. So I don't want to make a whole policy based on that person. I think that would be unfair for everybody, would screw everybody up. But I want everybody to know that if you happen to have, be in a situation like that person, then be like that person and just individually appeal to me and just don't lie to me and just don't take advantage of the system and blah, 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 blah. But that's sorry. So sorry, I totally sound like I'm angry. I'm not angry at any of you guys. I'm angry at the world that it makes us get so confused about stuff that we add even more stress to stressful situations. Also, I sound like I'm angry because I don't know how this is going to work, but it will. It will. So yes, if you have an individual circumstance, please contact me. Just like, by the way, just like if you have an individual request for a recommendation and you've been rocking the class and doing your thing, whether or not you got every question right, then you're going to ask me for a recommendation and I'm going to be delighted and honored. I'm going to say yes. And I don't feel like that means I have to write a recommendation for everybody in the class. I write one for everybody who asks me for one, right? Like that's fairness. Okay. Anyway, all right. Will there be, okay. All right, I'm back to the chat. There will be practice midterm like last time, but it's going to be faster than last time. Like I will try to give, I can't promise the level of solutions, but one thing I can promise everybody is you will know what's on this final before it gets posted. Like you will, that much I can tell you. I don't know, and look also to everybody, any advanced preparation I give you on the final is only going to make a difference of hours or days anyway. This whole thing is so fast. It's like I could give you the final right now and it would barely make that much, but you just look at me like we haven't learned the material yet, right? I mean, the 5-week course is crazy. Okay, that's why I sound like this. I never voted for it in the first place. The 8-week course was intense enough. I think the 5-week thing is crazy. We're just here because we're here because this is life. But this is not a way to do. But so we're just doing the best we can. Oh, then there's a direct track question. Sorry, God, I get myself. Oh my God. All right. Can you imagine having me as a student? I was such a wreck in school. All right. Is it possible to maybe release the final right after class at 4 p.m.? Oh, this is a direct track question. Is it possible to maybe release the final right after class at 4 p.m.? It is possible and maybe. I'm protecting myself when I say no later than 7 p.m. I'm honestly protecting myself. I'm saying no later than. Last time I was able to actually pre-schedule it for 6:30, like I computer scheduled it for, and it was like a half hour early. There is reason for me to post this right after class. And if I can, I will. But I think I also wanted to leave a little room for things to sink in for you, like for the class to end, for you guys to get the notes. Maybe like I wanted to leave a little room for things to sink in, or if there was questions. But yeah, it's possible. I'm going to do the best I can. I'm saying the latest is 7. I will actually try to get it up as early after class as I can. Oh, okay. Thank you. Thank you, Tomika. Thank you, Jean-Pierre. I totally appreciate it. Thank you, Antonio. I totally appreciate it. Thank you, Kirsty. I totally appreciate it. Thank you, Jacob. I totally appreciate it. Oh, here's a good. Oh, whoa. Oh, thank you, Shamari. That's probably not deserved, but I totally appreciate that, Shamari. Then, okay, by the way, quickly too. Oh, God. And it's really not, well, if I understand anything, is I understand how hard this stuff is for me. I mean, I find this stuff so stressful. And I'm here to tell you, by the way, or no, I'll get back to that in a second. But there's also a direct track question that's I can answer that maybe really issue. Someone said, out of all the material, I grasped everything except the homework 4 material. For the life of me, I haven't been able to attempt it. That is fair. Homework 4 is a very weird, like there was like a lot of practice on a lot of stuff that built, and then homework 4 was like a severe left turn. I'm going to tell you right now that some of homework 4, you'll see more and more clearly. It was really there to set up electric fields, which is now sort of, or fields in general, which is what the rest of the course is going to be about. So in some level, the rest of the stuff we do will retro clarify homework 4, but at some level, there's some stuff in homework 4 you'll never have to worry about again, and don't stress it. But if you're stressed about the points for homework 4, I will say when you get your midterm back, it might make it easier for you then to turn around and resubmit homework. Don't overstress homework 4. I mean, in some ways, you really already got the most confusing part of homework 4, you already got tested on in the midterm. And the most confusing part of homework 4 was really meant to set up the idea that all of a sudden, even with no springs whatsoever, with no pendulums, with just doing something funky with gravity, with digging a hole through a big round sphere, we could all of a sudden find like an invisible harmonic oscillator. Like it was meant to show that harmonic oscillator can pop up in the most bizarre or unexpected of circumstances. It was sort of meant to reinforce how pervasive harmonic oscillation is. And the example there was gravity. So the other side was meant to reinforce gravity, because we're now going to build fields from gravity. But in some ways, you already got tested on the hardest part of homework 4. So I wouldn't stress it, except for I know you might not ever get all the points on homework 4, but also for all of you, let me say the other thing. Remember all these homework points are not percentages. They're all just a pile of points you're trying to accumulate. It really is the whole, and like, even though the homeworks count more than the game turns, like if you entirely skipped one homework, if you entirely skipped like, homework 1 that was worth 200 points, you can get, all you have to do is find 2 or 3 game turn homeworks, like, like submit video for 5 minutes, submit that, and that's 100 points, and you get back your points that way. I hope you guys understand that. And like, nobody is going to get all the available points in the class. It's not a percentage thing. I deliberately put, and I'll put more, I deliberately put game turn portals in there that could only apply to a couple of people, like different ones, so that nobody could even think for a minute that it's about getting all the points in the class. You're just trying to get as many points as you can. You're just trying to beef up a big pile of points to help your grade. Like, they really are all, in a way, extra credit points. So I'm trying to tell all of you, like, while it's true on the one end that I will keep accepting back homeworks up until Wednesday, and hopefully, especially if you start thinking, oh, I think I get homework 2 now, finally. Oh my God, I think I get it. Like, do it and get the points. But if you don't do it, you don't get a 0. Or if you only did 80% of it, or if you only did 60% of it, you don't get a D. It's just a pile of points that you're all trying to get. And literally, you got to know it's designed so that you can all get a lot of them, but that nobody could possibly get all of them. So nobody should feel like, oh crap, I left a stone unturned. I didn't get 100% of all these extra points. No one's going to get 100. It's just a pile of points. Honestly, it's like a video game model of they're just like coins in a Mario game. The more you get, like, the better. But like, if you miss some, so what? There's more down the road. Okay, honestly. So if for chance one of you just like never turns in homework 4, that's not a crisis. It was just an opportunity to get points and also like to help you with the exam that you already took. That's for real. Okay. So sorry. So for real. Oh, wow. Now you're all agreeing with Shamari. That's okay. No, that's very nice of you. Okay. And yes, no, it's no. Okay. And now, even though oh my God, I'm totally, oh my God. Even though I took way too much time on this yesterday, also, like, there's another question in the direct chat about sorry. Sorry. There's another question in the direct chat about extra credit. Yeah, on the final, yeah, totally. There is, like, you'll notice after all my squeamish, I did put extra credit on the midterm. There's still more extra credit coming to you. Yes, and the exam will be more tight. And yes, and by the way, you're the sneakiest thing you guys do. If you ever want to like get me to agree to something or whatever, just saying, well, Professor Walters did this, totally works. Like, even though it's the worst, so I'm not like, mommy said, so like, daddy, can I do this? No, but mommy said, okay, totally works on me. Like, anything Walters does, yes, fine. I mean, whether it's because I love the man and worship the man and think the man walks on water, or because I'm in total competition with the man and God forbid you should like him more than me, whatever it is. And I do love the man, seriously, and the woman. Yes, I will. But just again, understand one of the reasons I get funny about the extra credit, if you really get the grading system, every single point you ever get on anything other than literally your raw score on the exam, which you haven't gotten back yet, every point is extra credit. In effect, all of it is just a pile of points. They are but yes, I got no problem giving extra credit. It's more of like a time management issue. I told you all that I was at Walters' wedding. No, I'll tell you that another time. Okay. All right, I will try my best to post the final earlier than 7 p.m. I will try to post it right after class. It's partly, some of these rules are just like what's possible for me to do or not. But yes, I will try. Oh yeah. I kind of answered it, but no. All right. So I'm looking at Catherine's last question. Yeah. Officially, please, anything other than the final exam, please, anything that you're going to turn in, please do turn in by Wednesday. We can say Wednesday midnight. That's fine. But please have anything else besides the final exam. Any old game turns, okay, cool. Thank you. Any old, thank you, Antonio. I mean, any old homeworks, just get them in by midnight Wednesday. And again, why is the reason for that? The reason for that is that so that by the time I turn around and look and get your final exams to grade and get your grades, and you will have had your midterms back by then, God willing, quark willing, electron willing. Like you and I both want it to be the case that by the time I sit down to look at your final exams, that's all that's left in your grading queue. Like, we both want that. You want to know exactly what your grade deal is before you take your final exam, which was an issue last semester in 203. Like, that's why you need to get your midterms back by Monday so that you know what's going on before you even take your final. And I need, like, once I'm grading your finals, I need that to be the only thing I'm doing. I don't want a million loose ends that I then have to tie up to come up with your grade. In the end, if there's any confusion or anything or any loose ends that are my fault, believe me, the tie will go to the runner. Like, when I'm in doubt about somebody, I don't punish them. I mean, I think you get that, but it's really true. And again, if you saw your grades from last semester, you'll see that that's true. Okay, cool. Okay, as long as we're talking about all this last thing, and again, like all the, no, and I appreciate that you seem to think that I am I really am trying, I promise. And one of the reasons I sound always so exasperated is I think enough things go wrong to make life hard. Enough things go wrong even when I'm not trying. Like in life, but also like I screw things up like I did last semester. There's enough that can happen just from circumstances that can give you stress or give you problems that what I don't believe in it therefore, all my efforts should be to minimize your problems. That's what I believe. It's not that I'm a nice guy. It's just, it's like a rational thing. Like, I know there's a type of teacher and professor in this world who thinks it's their job to decide exactly how hard to make your life. Like, they think it's their job to show you, like, to be like a military, and with all due respect to the military, but like that they think they're there to like strengthen you up and beat down your ego and show you how hard science really is. Like, I know, and I know you experience that a lot. And when I was a young teacher, to some extent, I thought that was my job too. Like, and but when I got older, I realized, like, oh, that's bullshit. I mean, I'm sorry, but it's just like, when people are when they think the art is how hard exactly to make it for you, to prepare you for life, what they don't understand, what they're really they're really just nervous about you recognizing how smart they are. Like, they're really just trying to prove, I mean, I shouldn't say this, but anybody who's spending a lot of time trying to decide how hard to make it for you is really spending more time than they realize trying to show you how much authority they have and how smart they are. And it's because they're worried about how smart they are. I mean, in my completely offensive opinion. I did that a little somewhat my first 10 years of teaching, and then I realized this is ridiculous. Like, all of this is hard enough. We don't have, like, it just is already hard. Our efforts together should be going to try to clean this mess up and like learn. So anyway, so it's not that I'm trying to be nice. It's just that I think things are going to, I'm just worried about things going wrong, even if I don't try. So why would I try to make things go wrong? Okay. Therefore, logistically, can I also say, sorry, and I mean it about the recommendations stuff. I've screwed up some things in my life. I've also accomplished some things in my life. Like, I've definitely done some things that I thought were really hard that I didn't think I could do, that I'm really glad I did, or studied some things that are really hard that I'm proud of. Like, I'm not saying I'm proud of some things that I know that I learned. But invariably, whenever I was able to do something hard, is because someone gave me the room to try and fail and do it my way and take my time. I've almost never been able to do something hard under conditions of somebody else, like breathing down my neck. And those of you who are in the military, like, I'm so impressed. I don't know how you do it. Like, I think it's awesome that you are that disciplined and that you can function in such an orderly space. Like, I mean, sometimes I can, but like, I find that super, super impressive and necessary, but it doesn't work for me. I need, like, if I'm going to do something hard, I need people to back off and let me mess up first and then work it out. And so that's kind of just what I'm trying to say to you guys. And I think the 5-week thing makes that difficult. To that end, last thing to warn you, let's say we get to the very final moment, like, and I have to turn in grades. And for whatever reason, either I've totally dropped the ball on something of yours that I was supposed to grade, or you've totally dropped the ball. Let's say we get to a point where all of a sudden, the night before I'm supposed to turn in grades, and I look at one of you and I'm like, oh my God, this person is totally going to get a D or an F. Like, I mean, I didn't even realize it, but this person never handed in the final. Or I don't even know this, like, this person's on my roster. I've never even seen them, or like something, or I've seen them, but blah, blah. If all of a sudden I know, oh my God, this person's going to get an F or a D. Now, some people are going to get an F or a D, and they know it, and I know it, and that's going to happen, and that's going to happen. And it sort of saves all the rest of you. That's one thing. But, and if it does, it's fair, it's life. Like, they know who they are if they just checked out of the course or whatever. But some people, I'm going to realize right at the last minute, oh my God, I did not give this person warning. Like, I don't know what's going on with this person, but there's a major communication failure here because, like, they never handed in the midterm or something. I don't believe in sudden shock surprises. So I will tell you right now, if all of a sudden I think there's a real disaster with your grade, and I don't think you know it, like, I think there might have been a communication ball drop, and I think this is going to be a major surprise to you, because it's even surprising and confusing to me. I'm telling you all right now, I'll say it once, and I hope you hear it. Under those circumstances, what I do is I give an incomplete. It's totally not what you're supposed to do. And more, we're really not supposed to do it, but it's what I do. I use incomplete to mean I have an incomplete understanding of what is going on here. Like, it's supposed to be for, like, you were in the hospital and therefore you couldn't take the final, and we all knew that. And certainly if that's the case, that's what I'll do. But if I have an incomplete understanding of what's going on, like something big is missing, and I have not reached out to you, or you have not reached out to me, and I don't, and I'm like, whoa, I will give you an incomplete, because to my mind, that means incomplete. Under the course is not over. There's something that has to be figured out here. And it may really be totally your fault. And you may really deserve an F in the class. But if I don't know it yet, and I feel like all of a sudden there's going to be a surprise or a possible like explosion lawsuit or something, I will give you an incomplete. If you get an incomplete from me, if you see incomplete on CUNY first, what that means is contact me, please, ASAP. And I don't know if any of you have ever gotten an incomplete before, but incompletes, they're meant for people that have a medical. They're meant for someone who like still has outstanding work, but everybody understands why, because like they're in the hospital. Okay. And the thing with incompletes, this is worth saying. Again, I didn't mean to get into all this now, but as long as we're talking about the final and everything, the thing with incompletes, just in case you've never got one or you don't know what they are, they can look really scary. I mean, if you see suddenly incomplete, you can be like, what? But what it means is that something still has to get worked out with the grade. And it means there's some arrangement being made between the professor and the student. And that as long as the work comes in by a certain short amount of time, the incomplete, once the work comes in and is graded, then the incomplete will be changed to whatever grade. Could be an A. It honestly could be totally an A. In fact, this happened to Professor Wu in a couple of classes because he got sick when he was a student. I mean, a long time ago. And then his incompletes were changed to A's. But when you have an incomplete, it means something has to be worked out. Then some work has to come in. Then the professor has to fill out a form. And I just did this for someone in the spring. I just turned in the form just now, like it does happen. And then they turn in a form that says change the incomplete to an actual grade. Could be an A, could be a B, could be a D, certainly. I mean, it could be a D, but it's whatever it is. And then the grade changes from an incomplete to that grade. And then from then on, it's like the incomplete never happened. The incomplete is just a pause. It doesn't affect their GPA. It doesn't affect their transcript. It's not a permanent blemish of any kind. It's just a pause in the universe. And if nothing gets resolved, if the work never comes in after a certain amount of time, then the incomplete devolves into a WU or whatever that scary thing is, or like the thing that's worse than a WU, I think. It will turn into a bad thing on your transcript if no one ever deals with it. And that has also happened in the past with students with me. But I'm telling you all right now, as long as we're having this whole big discussion, if you see an incomplete, do not freak. Do not think your life is over. Do not think I'm out to get you. Do not think there's a horrible misunderstanding. Think, I need to contact Yaverbaum, ideally by email, and just politely contact me and just say, I see there's an incomplete. Can we make an appointment to discuss? And I will politely, we will both give each other the benefit of the doubt, and we will find out. I'll be like, well, yeah, the deal is like, did you ever turn in a final? Because I don't have one, or whatever. And then you'll need to be like, yes, oh my God, I put it in the wrong portal. Or you'll be like, oh no, okay, I totally should have, is there still something I could do? And I'll be like, yes, there is, but like, we're gonna have to be strict about this and yada, yada. So the incomplete means we have a talk, we figure out what's going on, we figure out who's missing what, and we make an arrangement. And depending on the circumstances, it could be that it turns out, no, you totally, okay, well, no, or it could turn out that you get an A. But if you get an incomplete, it means you have to contact me. And I will say that, and you have to stay on. You have to make sure I respond to you. As long as you do and we work it out, it'll all be cool. It may totally have been my fault and all of that. And we'll both be respectful to each other. But if you do get an incomplete and you never follow up with me, I'll never do anything about it. And it will just turn into a WU. So it is kind of my it is my way of saying, hello, are you out there? Are you out there? Here's your extra delay. Like here's their last waiting period to come to Papa and deal. Okay. So if you get an incomplete, do not panic and do not be angry. Just email me politely and I'll email you back politely and we'll take it from there. Okay. Oh my God. Okay. This is a guy who supposedly liked school. Okay, all right. I'm gonna take a breath. Okay, we're gonna move on. So sorry. These are all fair questions. I love you all. Okay, we're gonna go to this. Yes. Okay. Also, can I say, I've said this before. I've gone to college. I've gone to graduate school twice. I did science. We all know it's hard. I also did philosophy. That's hard in a totally different way. I did hard stuff, right? But you guys, your program is so freaking hard. Really, I know. I mean, if you can get through this John Jay science program, and some of you are coming from other programs, but the programs we're in are so hard and they're so much harder than a lot of ritzy, private, expensive programs that a lot of people have heard of. I know that. and I want you to know that I know that what you're doing is so hard and so sometimes unfair. If you get, it's worth getting through this program. If you get through and you get a degree, what that degree says above all other things is this person did something that a lot of people cannot finish. Like give this person a job. That is what your degree says, and or give this person an entrance to graduate school. And I freaking really mean that. Like whenever it feels hard to you guys, you're right. And whenever you feel like, oh my God, am I even belonging in this program? Should I drop? Maybe I don't even belong here. The first prerequisite for being in this program is that feeling at some point of feeling like you don't belong. There's nobody that doesn't hit the moment with like, oh my God, do I belong here? Or the moment of, I guess I belong here, but is this really worth it? If you're going through those moments, the answer is yes, just keep going. Just keep going and it'll be fine. Okay, so back to fields and field lines. Okay, back to material from yesterday. Now I just want to, am I going to change what I was going to do? Just think for a second. All right. Okay, this is a little bit of, before we get back into all this like electricity stuff from yesterday, I want to remind you of Monday's lecture was a big long lecture. You have the notes from it. The YouTube recording of it is lost now, so this will go into like the Arceus legends of whatever. We'll have to get like Hop and anyway, whatever. But the conclusion of that whole lecture, the conclusion, we were spending all this mathematical and physical time driving at getting this wave equation. The conclusion of that whole lecture was a second order partial differential equation that's meant to look very much like our Hooke's law differential equation. I mean, it's very much like but it's like a little bit harder, right? Like it has a second time derivative on the left, then it has a equals a constant, happens, this one happens to be a positive constant, not a negative constant. And then next to that, whereas with Hooke's law, we have just the variable like displacement from the equilibrium position. Here, we don't just have the variable, we have a different derivative, a space derivative. It is one step more complicated than Hooke's law. It is saying that a wave ripple is a bunch of Hooke's law oscillations happening both in time and in space. Like that is what we're saying, right? But that's one way to look at it. But whatever it is, this is the equation that describes all wave pulses, right? Now I want to say, and you are responsible for that. This is the mathematical way to describe a wave pulse. I want you to remember that a wave pulse is already interesting. It's like worth having its own equation. It's worth looking at as its own thing because it's a thing that moves through space and time, but it's not a thing, right? It is, as it says, so you probably can't read my handwriting actually, but it says under the wave equation, it says wave motion is the transmission of immaterial information. Let's just pause it. That's what I'm trying to write there. Wave motion is the transmission of something immaterial, right? When a wave pulse goes from here to there, there's no material or massive or particular or discrete or identifiable or tangible thing that goes from here to there. Again, like the classic example, sound. When sound goes from my mouth to your ears, no thing goes from my mouth to your ears, yet something goes from my mouth to your ears. What goes when sound goes? Well, some people will say energy. Sure, you could say energy travels, but that's a very abstract word. I mean, I'm not even entirely sure what it means other than saying it's a thing that's not a thing. I mean, technically energy is the ability to do work. So the ability to do work is going from my mouth to your ears. Well, yeah, at some level that's right. I just don't know how helpful it is to say that. Like if nothing else, recognize that if you're saying, oh yeah, when sound travels from his mouth to my ears, I know what's traveling. When any wave travels, what's traveling is energy. If that gives you comfort, if that makes you feel like you understand what's going on, good. But that's, I assume that when you're comfortable in that, you're comfortable in the idea that energy is a word for something that's not material. You are comfortably putting in a word there to remind yourself that whatever's going from my mouth to your ears when I talk is not a thing, right? It's something that matters, but it isn't matter. So as long as we're going to use abstract words for this immaterial thing, and again, by the way, if I had room on the notes, I might write like what a wave pulse is, or what energy is, or what are things that matter in the universe, but aren't matter. So another good word for that is information, right? This is the big thing I want to pause, why I want to back up for a second and say, especially since that lecture got lost or whatever. What's traveling when a pulse travels along a string, or when a sound travels from my mouth to your ear through air, or when a ripple travels across the surface of the ocean, like at Coney Island or Rockaway Beach or whatever. What's traveling is information. That's the word I think that's the most powerful, like concrete word, especially for our generation. For the 21st century. What you're sending is information. You're sending like concepts, facts, numbers, quantities, vectors. You're sending numerical truths from one place to another when you send a wave pulse. And you're like specifically, like if I sing the note A, or if I play the note A on a piano keyboard, what I'm sending to you is a vibration of 440 hertz. Like literally, I mean, that is literally, do I have, oh, it's downstairs. If I played a piano key right now, literally middle A on the piano, then on a real piano, let's, I mean, I don't, oh, someone's here. Say on a real actual like acoustic piano, play the note A. Then the hammer from the key slams down on the string inside the piano. The string will vibrate at literally, truly, this is not a random example, it's the true example, 440 hertz, 440 cycles per second, the string will. If it's a middle A, if it's middle C, it'll be like 256 hertz. I mean, for real, these are not made up numbers. This is what it means to be a C or an A or whatever. Then that string vibrates the air molecules around it at 440 cycles per second. Now, first it was a string, and the thing that was vibrating, the material set of particles, the collection of material particles, what we call string, is the medium. Like the first, like that vibration will pass through the medium known as string. Then it'll pass from there to the air, which is a different medium, a different set of particles. And the truth of the matter is the particles in the string will vibrate in what we call a transverse way, like they'll oscillate up and down along axes that are perpendicular to the axis of the string, hence the Y's and the X's in this equation. Then they'll hit air molecules, which in truth actually will vibrate along the same axis. There's just detail, you'll never be tested on this, but it happens that then the air molecules will vibrate in what's called a compression format rather than a transverse format, which means that each air molecule, instead of going up and down and then up and down and up, it'll push side to side to side. It'll make little pressure packets, but detail. And air molecules are a totally different material from string, but those air molecules will vibrate, vibrate, vibrate. Then that vibration gets to your ear. Then the cartilage in your ear, or the eardrum, will now vibrate. Now, totally different medium, totally different material. It'll totally vibrate in different format, but then that will set off electronic vibrations in your brain, which is what I want to get to eventually with this. And electronic signals and electronic currents will travel through your brain, totally different medium. Now we're talking electrons, totally different shape of this vibration, totally different wavelengths, all these other parameters. But the one thing that will be true all along is that it'll always, if I played A on the piano, middle A on the piano, then what will be true all along is that the vibration rate, the standard frequency, will be 440 cycles per second. And when that gets into your brain, or if it was middle C, it'll be 256 cycles per second. And when it gets to your brain, if it is indeed 256, that whole journey through string, through air, through cartilage, through electrons, what will be preserved the whole way through all these different shapes and bizarre phenomena will be that things will go back and forth, back and forth, back and forth at 256 cycles per second. And if that reaches your brain properly, you'll be like, oh, that was the correct note. Like if you actually know music or have perfect pitch or whatever, you'll be like, oh, C natural, middle C natural. How lovely. Thank you very much. Oh, but if it was but even if you don't, and it was in the context of a song that you like or that you know, even if you don't know anything about music theory or pitch, but you know the music you like, if it reaches your brain correctly, be like, good, yeah, they played it right. Yes, good. But if it's like slightly off, if it's like some fraternity band playing like your favorite band song, whatever, and they blow it and they sing the wrong note there, it's slightly wrong, like slightly flat or slightly sharp, i.e. they send a vibration that's not 256, but like 246, even if you don't know anything about physics or math or music theory or anything, if they hit a sour note, you're gonna be like, oh, right? You're gonna be like, that's wrong, dude. Whoa, that is not what you were supposed to play. You might not have the words for it, but you'll know it's wrong. What will you know is wrong? You'll know that it was supposed, like you don't know what you know, but your brain knows, we were expecting 256 hertz of standard frequency vibration and we got 246, wrong. What am I trying to say with that whole long example? I'm saying waves are waves are unbelievable. Every time we send one note, what we're sending is a number. That's what I'm saying. When you send a wave pulse from here to there, even just one wave pulse, what you're really sending is a freaking number, a number. And that's what gets to the other side, even as like the medium will change from string to air to cartilage to electrons. Somehow what gets preserved all along is the numerical rate of vibration. And when that lands, it either registers as landing correctly or incorrectly. That's what gets to you, is a number, which I'm now calling information. It's something that matters, but it doesn't have matter, okay? A wave pulse is that. It's an immaterial, it's a transmission, a conveyance, a traveling, a journey, a propagation of immaterial information. Wave pulse is information. And the information travels through a material thing that we call a medium. Like the medium is the collection of material particles that we need for this phenomenon to occur. I'm reminding you of all this because I want also to relate this back to the electricity thing that we have to do, okay? But I'm also reminding you because the lecture got lost, so I want to make sure this is reinforced. So I want to unpack this. So we're staying on this for a second. I know this is a little bit confusing, but I'm backing up to material from 2 days ago. It also relates to the lab. Okay, so I want to look at this equation for one more minute or so before I go back to electricity. Again, it is all related in the end. Hopefully you'll see how it's all related in the end. But every time I write it slightly differently. And I'm sort of doing that to keep you on your toes. I mean, I don't want to confuse anybody, but notice here I put the squares inside because sometimes that's helpful and makes it clear. Here I put the square. Sorry, hello. Here I put the square outside. It's totally equivalent. I'm just making that choice. You know, you do want to be sort of that flexible. And if you don't like it, you could you could put it both on the outside for both times, but I want to keep it on the outside for this time. Okay. So quick thing, again, I mean, and again, I'm saying this looks like an intimidating equation. Okay, if I just saw this out of context, I would be lost. I'd be like, what? Okay, I don't even understand one symbol in that equation. But at this point in the class, kind of hopefully you do think of it in chunks, right? The whole left side chunk is just a second derivative of position with respect to time. Like, yes, they're funny new symbols. They're the funny new backward sixes instead of Ds. But those funny symbols just mean partial derivative. They're just like derivative, but they're the symbol that we use whenever we have a function of more than one independent variable. Like those things mean the same thing as lowercase d. They mean differential, instantaneous rate of change. We use them now because we now have a function of both time and space. So that's number one. So the whole left side is just second time derivative of y, i.e. acceleration. The whole right side thing that's not in the parentheses is second space derivative, which in math class is known as concavity, right? So just to remind you, the wave equation is complicated in a way as it looks. In a way, it's really simple. It's a direct proportionality, just like Hooke's law was. It's saying one kind of derivative is directly proportional to another. It's saying that if you're sending wave pulses back and forth on a long string, pick any place and time on that string, any point in space and time along the medium, like the string is the medium. It's the collection of material particles through which the pulse propagates. This equation is saying pick any point you want in that medium at any moment, and look at that point, the rate at which it's accelerating back home, back to equilibrium axis is directly proportional to how deformed, how concave, how perturbed, how misshapen the string is at that point. In other words, if you picked a point that was right on the axis, if the string's not misshapen at all, then nothing's happening. Those are equal, like that's an equilibrium spot. That's where things want to be. But the more bent a chunk of the string is, the faster it unbends itself and races down. That's literally what wave motion is. Let me put it another way. When you watch a pulse move along a string, what I keep trying to say in different words is when you watch a pulse move along a string, you're not watching a thing move along the string, right? All you're seeing is pieces of string moving, but the pieces of string are not going left to right. They're going up and down. So what is it that's going left to right? It's a disturbance in the shape of the string. What you're watching go left and right, what you call the crest or the trough or the pulse or the whatever, what is that? That's a deformation in the medium. If the whole medium stayed flat the whole time and preserved its equilibrium shape, you'd be watching nothing. What you're watching is concavity pockets in the string. You're watching a little piece of string that is not flat, but rather concave. What this equation says is the more concave you are at a certain point in space and time, then the faster you'll rush back to non-concavity. It's like Hooke's law. Hooke's law says the farther you are from equilibrium spot, the faster you rush back to the spot, right? That's what acceleration equals k over m times x. Like that's what that means. This we're saying the more bent you are, not like the farther you are from a spot, but the more bent the whole string is relative to flatness, the more quickly that bent piece will race back to flatness. Okay, so that's what this equation is saying. Now, what I'm saying is, okay, so therefore omega squared over k squared, or omega over k squared, that whole piece is a constant. It's a constant over constant squared. So it's just a constant. It's just saying like why it's like we're saying y equals mx plus b, but b is 0, and that whole piece is like m. So in a way, mathematically, it's just a constant in proportionality. But it is composed of omega and k. So what I want to take a moment, I'm taking way more than a moment, of course. I want to look at that constant for a second and remind you of something about that constant. Bear with me for 1 second. Okay. So I'm going to turn the page. Let me know if that's bad. But so again, this is all kind of an interlude, but I want to unpack that constant for a second and say what it means. Mathematically, it's just a constant, just like omega squared, or just like k over m in our original Hooke's law thing was just a constant. But our original Hooke's law thing, k over m, meant something. It was like spring stiffness over mass. So does this thing here mean anything? The answer is yes, it does. Sorry. Just to remind, partly to remind, oh, sorry, chat. Hold on a second. Oh, right. Okay, cool. Thank you. And oh, so K, yeah, K is the new thing from like lab 3 and lab 4 and from lecture Monday. But K, this K, technically is called angular wave number. Okay, K, so K is angular wave number. And I'm actually kind of trying to explain it right now or remind us what that means. K is to space. So what it's called is angular wave number. Just like omega is called angular frequency, K is called angular wave number. K is to space as omega is to time. Like omega ultimately is how many cycles there are per unit time in a wave pulse. Like, so how many like if you were drawing out the cosine graph, like how many humps, how many crests in the cosine graph there would be for every second, but measured in radians. Like, so how many full cycles we make, saying that there's 2 pi radians in every full cycle per every second. That's what omega is and was. That's what omega was back with just regular masses on springs and continues to be for waves. K is now comes into play. Like there was never this K with Hooke's law. This is why this is a good question. But once we put a bunch of oscillators together and we make a wave pulse, then there's K, because K is the number of cycles per space. Like what we're saying is that a wave pulse is oscillations occurring in both time and space. What we're saying, the purpose of lab 3 is that if you send a wave pulse down a string and you make a movie of that, then with that movie, you could do one of 2 things. You could either focus on any, and I think this is what you did do in lab 3, right? You could take this movie of a wave pulse and you have choice number 1 is you focus on some horizontal spot along the medium. You prick some spot and maybe you line up a ruler next to it or some y-axis or some piece of tape next to it. And you pick some spot and you let the movie go and you're like, okay, where, and you pick that spot on the medium, like on the long coiled string or spring or whatever it is that's like shaking up and down. And you pick that X spot and you're like, let the movie run. And you're like, okay, where's the spring right now? 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 Oh, where's the spring right now? Where's the spring right now? Where's the spring? So you watch the metal as it goes up and down in its y-axis per unit time for some fixed unit of space. That's like one option, right? And if you were to watch that, you get y as a function of t, and you have an omega, the number of times the thing goes up and down per second, because like you see a little oscillator there. we're saying that if you pick any little section of a wave pulse, what you see is if you pick any little section, any little section of a horizontal wave pulse of a horizontal medium, you'll see a little vertical oscillator going up and down. And you can pick any one, right? And if you graph what's going on up and down, you get a cosine graph. But we're also saying at the same time that if you just pick a time value, if you just pick one moment, in other words, just take one frame from your whole movie and step back and look at the whole thing and just say, instead of watching one little piece go up and down against the clock, if we freeze the clock, if we pick a time value and just let our eye look from left to right and go like, okay, I'm looking at the left part of the spring of the medium. I'm looking at the next part of the medium. Look, you would notice that the spring, like the left part of the spring is over here, but the next part is over here, and the next part is over here, and the next part is 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 here, right? In other words, and I know I'm saying this as many different ways and times as I can, because it's such a deep thing. Once you get it, you'll see what I'm saying. I'm saying that wave pulse combines oscillations with oscillations. We have y as a function of t, and the constant of proportionality for that is called omega. It's cycles per time, but also there's cycles in space. Like even if we freeze time, there's like a hump of the wave here right now, and there's a crest of the wave right over there right now, and there's a crest of the wave over there right now. So there's a number of humps per unit space. We call that k. Okay, k is, if omega is the number of cycles per time, then k is the number of cycles per space. They must both be existing if we have a wave pulse here. Put a flip way now to, hopefully that's sort of answered. But, and again, just to everybody, k is the hardest of this whole topic of all of simple harmonic oscillation, all into waves, of homeworks 1 through 4, of labs 1 through 4. The most reasonable thing to ask questions about by far is k, because k is definitely the last thing you learned. K is definitely the last piece in the puzzle. Don't pretend you understand it until you do understand it. Like nobody should be ashamed of still being foggy on k. Every time I talk about it, I'm trying to teach it more, but k is the newest piece of all this. What I'm saying is you can understand k by analogy, hopefully, or maybe it forces you to retrospectively understand omega better. Like k is to space as omega is to time. And let me put it a different way now on this page. What I'm saying is, oh yeah, like omega was like 2 pi per period. Like omega was how many cycles occur during every one period, like how many radians are undergone during every one period of time, and a period of time we call capital T, and it's measured in seconds, right? Well, in other words, T is the amount of time for one cycle. Similarly, we have a thing called wavelength. You've known about it your whole life. I think it does come up in lab 3 and lab 4. I've never literally said it before here in this class, but what is wavelength? It's exactly what it sounds like. Honestly, just like, I think wavelength is the one thing that you've known about from other classes or can picture, and I'm not trying to trick you with it. Wavelength is like if you freeze any wave. Okay, cool, awesome. Thank you, direct chat person. That's totally helpful. If you take a freeze frame of a wave pulse, or if you ever look at a graph of what's happening on the y-axis as a function of what's going on the x-axis, the distance between any two neighboring crests, or equivalently, the distance between any two neighboring troughs, the distance from one cycle to the next is the distance of the wave cycle. It's the length of the wave cycle. It's called the wave length. I'm not trying to be obnoxious. Like it's the one thing in all this that kind of does make sense. And it's designated with the Greek letter lambda. Hopefully that was true. Like, again, I've never actually said that before. I'm saying it now. We use lambda to that Greek letter that's circled here, this letter. Lambda is what we use to designate wavelength. Wavelength is measured in meters. Wavelength is the spatial equivalent of period. Period is the number of seconds in one cycle. Lambda is the number of meters in one cycle. Okay, we're trying to say that at any given moment in a wave, what's happening in space is what's happening along the x-axis is perfectly analogous to what's happening on the time axis. That's the nature of this kind of transverse wave, that x-axis of space and the t-axis of time are both contributing the independent variable information that drives the dependent result of how high the darn thing is. Okay. So if you sort of understand what's going on in time, we're saying that's also what's going on in horizontal space, or vice versa. So T is period. It's the amount of time for one cycle. Lambda is the amount of space for one cycle. Period is measured in seconds. Wavelength is measured in meters. The reciprocals of them are omega and K. So if you kind of understand period, omega is just the reciprocal of that. And by the way, that's something that most of you totally did seem to understand like 2 days before the midterm, and do seem to understand on the midterm, like what a lot, like in homework 3 or problem 2 of the midterm, the whole temperature thing. I think a lot of you really did have it by the time we got there eventually. Like, and people have literally said in the chat and in the class, like, oh, that's the omega equation, or that's the period equation, that whole business. And there's like a million different ways to write it. But that omega equals 2 pi over T, that's a time, just 2 different ways of measuring the time of a cycle. If you know one thing, you know the other. Same thing with K and lambda. They're just 2 different sides of the same space coin. Now, and I'm saying all this, I am saying more than, I mean, I do have to get back to the other thing, but I'm saying all this for a reason. I'm going to put these 2 things together to show you something. Like, hopefully you vaguely get what I'm saying, and I'm not going to test you on this as such. You don't have to do a million problems to solve this. Just if you're sort of following, I'm going to put these 2 things together algebraically to show you something that's, I think, super important. But first, these commercial messages. Hold on, the chat. One second. Things are happening in chat. Oh, good. Thank you. Awesome. Oh, you had a board meeting today. Oh, that's actually really helpful too. So did you have the board meeting on Doppler effect today? Is that what you had? Awesome. Oh, then, that's great to know. Great to know. And cool. First of all, I don't know if you liked it or not. I know board meetings on Zoom are a little bit torturous. I do get that. I mean, they used to be my absolute favorite thing of all time. Like I used to live for board meetings. I still do in principle, but I understand on Zoom, they are what they are. But I'll tell you this, I felt a little guilty dealing with this right now because I kind of want to get back to the electricity thing. But, oh, good. Awesome. And don't get, no, when they're good, they're good. I'm really glad. And if you got anything out of it, and even if you're still confused, I'll tell you all right now, if that's what you did in lab today, then what I'm doing right now is super relevant to that. Like, that actually makes me feel better about what I'm doing right now. You'll see in a second how it's completely relevant to that. Even though I know you don't have to do a report on that or anything, but still. So, and then we'll get back to the electricity. And then I know the rest of your labs are on circuits. I mean, anyway. So here's what I'm saying. Omega is like cycles per second. K is cycles per meter. Therefore, Okay, this is huge. Chat. Sorry. Oh, cool. Right. Okay. This is huge. This is where, again, I'm a little bit like going out of a kind of a funny order, like, and I want to get back to electricity, and we do have an hour to do that, but I just can't do the course without pointing this out. And hopefully we get to everything and all the course comes full circle. And yeah, but like the wave equation says that acceleration at any given moment back home is directly proportional to concavity from home. Like how deformed the string is at any moment determines how quickly the string rushes back to flatness. And that's true at every single point. So everything is alternating in that pattern, and that alternating pattern of patterns gives you a wave pulse. Okay, but the constant of proportionality, that parentheses omega over k squared thing, on the one end, it could just be a constant, and it could just be like a random number, and that would already still be an interesting equation. But what we've just shown right here, just by looking at the definitions of omega and k, what I'm really saying is omega is cycles per time, k is cycles per space. So omega over k is cycles per time over cycles per space. And I know it's a little fuzzy, but if you remember, if you think about math, when you divide fractions, you multiply by the reciprocal, right? I mean, I know it's like fractions within fractions, so it can make your head swim. But if you're careful about it, you'll see that 1 over t divided by 1 over lambda just flips everything and gives you lambda over t, gives you, or what you might call in lab, what you might have called in lab, I might add, it might be easier. This is the same thing, and you'll see this in books all the time. Lambda over t, wavelength over period, is the same thing as wavelength times standard frequency, which that's the way it's often in books and in other classes. You can write it down either way you want. They're totally equivalent. But here's what they mean either way you write it. It's space over time. What we're saying is that omega over k is the amount of space for one wave cycle divided by the amount of time for one wave cycle. So we're literally saying, like, say that you're standing at Far Rockaway or Coney Island, where the water's coming in, right? And you're like, and you notice, like, oh, there's 6 meters between every, from every one crest of wave that breaks on the sand to the next crest of wave that breaks on the sand. Let's say you notice or you measure, there's like 6 meters between each one. And you stand there with a stopwatch because you're a loser. No, because you're like me, and this is what you do with your children. You're standing there with a stopwatch and you time it. So it's like one crest comes in, and then you start your timer, and then 1 Mississippi, 2 Mississippi goes, and the next crest comes in. I'm just making up arbitrary numbers, but in other words, say you measure, and pretty much consistently you get like 6 meters between the wave crests, and you get 2 seconds of time between the wave crests. Then what are you finding? What are you saying? You're saying that each one of these crests is traveling at an average, but in fact constant speed of 3 meters per second. Like that constant, in other words, that constant in the wave equation is the propagation speed of the wave. And that's like not the rate at which anything like oscillates up or down. Those derivatives are changing all the time. We established on homework 1, right? Any given piece of water, if we're looking at water waves, any given piece of water is going up, down, up, down, up, down, and it's got a velocity and acceleration and a jerk that are changing continuously all the time. There's nothing constant about that. But together they form this pulse that's going horizontally in the water or on your string or whatever. And that horizontal pulse is propagating at a measurable, analyzable, predictable speed, a speed which is actually simply embedded in the equation at a speed that is constant. Like, so what I'm saying is, well, yeah, wait, I'm going to take one more page on this. I'm always afraid to start this point because once I get going on this point, it freshly blows my mind every time. So it's like hard for me to get away from this point. And I'm being genuine. Like this blows my mind every time I think about it. And I've been thinking about it for 28 years or whatever, like 3 times a day. And I always try to bore myself in advance. I literally try.
Professor,
Yeah, sorry. Oh, back.
sorry. Yes, please.
Absolutely. Okay. No, and see, I can lose my mind. I mean, like, sorry, I'll stop for a second.
Okay, you can move to the previous page. I just needed to end.
Oh, cool. No, if anything, no problem. And if anything's worth writing everything down, it's definitely this. I'm just seeing what I'll catch my breath. Okay. Yeah, like, no, and again, I know it's a little confusing because I'm going back to something from 2 days ago, and this is not directly, it's not clear how this is related to electricity yet, although it very much is, believe me, it is. But the point that I'm making here, which I always try to I always try to tell myself it's boring before I say it so that I can say it in like a shorter amount of time, but I just can't. Like what we're saying here is if you arrange a bunch of little oscillators vertically to go like, even just like if you all go to Yankee Stadium or whatever they call it, or City Field or whatever, and you do that, or the Olympic, whatever. If you all got in the crowd and you did that thing, like I stand up and then I sit down and then the guy next to me stands up and then sits down and then the person next stands up and then sits down, right? Everybody's like, oh, that's like the wave. That's the human wave. Let's do a wave. I don't even know why I'm doing air quotes or rolling my eyes, because the fact is it totally is a wave. Like that's not imitating a wave. That's not pretending to be a wave. That is a wave. Like that is a perfect demonstration, especially when you do it well. That's a perfect demonstration of that's a perfect demonstration of a bunch of human beings acting like the medium. A bunch of human beings are the material particles now. Each human being is just oscillating in its little neighborhood. I mean, they might not do it perfectly harmonically, but each human being is oscillating like vertically in its little neighborhood. And they're moving in a pattern, right? But if they pattern their pattern with everybody else's patterns, right? So I'm in a pattern, up, down, up, down. The person next to me is in a pattern, up, down, up, down. But we're also well, that's what I'm trying to explain. Right. I mean, good question. What does that mean? I mean, I think if you mean, right, this is what I'm trying to explain, is that if you mean, wait, let me, yeah, hold on. Yeah. All right. What I'm trying to say is that a wave pulse is a collection of staggered oscillators. It's a pattern of patterns. It's a bunch of little particles all put together that we call a medium. And each particle is acting in a pattern. But then each pattern is patterned together. Like I stand up and then I sit down, or if I'm a piece of string, I go up and then I come down. But next to me, something is going up and coming down, and next to it, something's and we've arranged it all so that we're not doing that randomly. Like we're not doing it all at the same time, where each person's waiting the specific amount of time. And right, and the fact that you can all do this in Yankee Stadium without knowing the math or without like having a big planning meeting means even instinctively you can sort of do it. Like you know to wait until it's your turn to go up and then come down, and then the next thing waits till it's its turn. And the more patterned these patterns are, the better what ends up happening is we send a pulse horizontally through the people, right? Each person only goes up and down, but something, the ripple, the wiggle, the whatever travels left and right through the people. That's a wave pulse. And what I'm saying now, what I'm trying to say here in red or on the page, is that actually that speed at which the pulse travels, that distance per time, that average velocity, you want to say, that speed that at which the immaterial information ripples through the medium, that speed is first of all what we call the propagation speed. It's not the oscillation speed, it's the propagation speed, or the propagation velocity, or some people even call it the phase velocity. But that speed is apparently constant. It's a constant. Like I'm trying to show that what this constant in the equation is the wave speed. But the more important way to put what I'm saying is this shows that the wave speed is a constant. I'm trying to say that once you start wiggling a piece of string to send pulses going back and forth, no matter how hard you try or don't try, no matter what you do with your finger, the the pulses will go at a certain speed that is fixed, that doesn't speed up or slow down, that we could predict even before you started doing it. Like, I'm trying to say that the speed at which a pulse propagates through a medium, the speed at which we send information through the air, for example, or that we send a ripple through a long string, I'm saying that speed is a constant speed, a reliable, predictable, unchanging speed. And it's which is already like makes our math a lot easier. Means we don't have to worry about 1f(at) squared. We don't have to worry about acceleration, but also means we can make predictions, and we much easier. We can rely. This is why we use waves to do what we do. This is why we transmit information through waves, because they're like on permanent cruise control. What I'm trying to say here is the speed at which a wave pulse propagates is a constant. It's that constant, and more the constant called omega over k. Last specifically, yeah, okay, I'm gonna once again, I'm gonna do this on the next page because it's too important. Sorry, I wish I had what I'm saying right now, and then we will wrap this up, this point up. I'm saying the speed of propagation of any wave, like, again, why all this math happens. Like, I love math at this point in my life. Some of you may not like math as much, but why does the math happen? Because the math is an attempt to show what's true about any of our examples for all examples, right? The math is the underlying truth that is just universal, that doesn't get bogged down in exactly how strong the coil of metal is or whether it's metal at all. It's just the nature of the relationships, right? So what I'm saying here is that any wave pulse at all that you can picture or send, that you can, like the wave pulse you sent in lab 3, or the wave pulse that you made up in lab 4, or the sound wave pulses that you were discussing in the board meeting, or water ripples on those, any wave pulse that you can picture. What I'm saying now is it's got a speed that is entirely determined by omega and k. Its propagation speed is omega over k, or if you want to call it lambda times f, as you might have been doing in the board meeting. The propagation speed of a wave is a constant, first of all, like that's huge. Like, it doesn't speed up or slow down, but it's more than just a constant. It's a constant that is dependent on parameters. Like, remember, I'm saying the speed of a wave here is omega over k. Oh, and there are two different k's going on now, but remember that old omega in a simple harmonic oscillator was, like, for a mass on a spring, was square root of old k, Hooke's law k, over m, like the k that doesn't have, this is not a typo, like it is two different k's on the page. One has serifs and one doesn't. Remember, our good old omega was square root of k over m. We made a big point. I made a big point one day and then started talking about Galileo and the chandelier and everything. And then we got off on calculus and not off, but then that's what that day turned into, calculus and the chain rule and all that. My big physical point that day was that for any given oscillator, it doesn't matter how you set up the oscillator. It only matters what it's made up of. And you'll know from the start the rate at which it will go back and forth and back and forth. Pendulums go back and forth at a certain rate, regardless of whether you hold them out here or you hold them out here. That's why they work as clocks, even as the swings are getting shorter in space, even with the real world addition of friction, even as a chandelier is having smaller and smaller swings, it doesn't really lose time. A swing of this size or a swing of this size, both each have a tick rate of the same number, because energy is conserved, blah, blah, blah. Like, the angular frequency is determined solely by the parameters, by the physical properties of the oscillator. That we established that was true of omega like weeks ago. And I'm saying now the same exact logic applies to any other angular constant in these oscillations. In other words, k. Omega and k are constants that are totally determined by the material properties of the oscillating stuff, the oscillating particles or whatever. In other words, what I'm saying, and I hope I'm not going to the next page too fast, I think this is the last page on this point. What I'm saying is, I'm saying that the minute you fix a medium, the minute, and what is medium again? Medium is the collection of material particles, every one of which is oscillating in a small neighborhood, and together which make up the whole phenomenon of a pulse. Okay, the medium is the collection of material particles that are all moving in a pattern of patterns in order to make a wave pulse. Once you know what your material is, what your medium is, you know its material properties, you know its parameters. Like, so if it's a bunch of little metal springs, then you know the K of each spring, the stiffness, and you know how much mass is on each spring. Or if it's air, then you know that it's made of air molecules, you know how springy or stiff air molecules are. This kind of goes back to homework 3, where you know, in other words, the temperature and the pressure at which those air molecules are resting. If you know those parameters, it's like knowing how stretchy a spring is. Once you know how stretchy the spring can only go up and down at a certain rate, which then in turn means that pulses can only go across at a certain rate. Once you know the properties of your medium, you automatically know the speed of wave propagation, which is huge. Ultimately, it's this V equals lambda F thing. It means, like, if we take this long string and stretch it between me and you, I can try to go like this. I could try to make wave pulses by going like, I'm going to make really fast wave pulses. And what I'm doing by shaking my hand really fast is I'm making frequency of pulses very, very high. I'm generating a lot of pulses per unit time. I can do that. I can make a really high frequency wave. But I can't affect the rate at which the wave pulses will go through. That's fixed by the medium itself. So if I go like this, I'm going to make really, really high Fs, but I can't do anything about the V. So what that will in turn mean, this V equals lambda F, is that there'll be really low wavelength waves. If I go I'm going to get a lot of really small pulses. Or if I go then I'm going to get very few big pulses. I could do I can make F high and then lambda will be low, or I can make F low and then lambda will be high, but they will always adjust with each other in order to ensure one constant V. No matter what the speed will travel, the wave pulse will travel along the string at some speed relative to that string that I would know even before we started, as long as I knew enough about the string. Just like you know that sound will travel from my mouth to your ears at 340 meters per second, simply as long as you assume that the sound is traveling through air at standard temperature and pressure. Like as long as you know what the medium is, you know what the speed is. This is why we can talk about things like the speed of sound, like why there is even such a thing. Like there's no speed of a baseball. Like like I could throw a baseball at 75 miles an hour. Someone in the class could throw a baseball at 85 miles an hour, and then tomorrow they throw it at 63 miles an hour. And you can throw baseballs at any various speeds and you can barely control it. And by the way, while the baseball is traveling, it doesn't maintain a constant speed, right? It'll be falling while it's traveling and it'll be speeding up, therefore, due to gravity. So baseballs don't travel at a given speed and they don't even maintain a constant speed while they're traveling. So we never say things like, you could say, what was the speed of that pitch on average from the other day? But you don't look up the speed of a baseball in a book. There's no such thing. And you don't look up the speed of even a car. Like you can look up the maximum speed that the car could go, but cars go all kinds of speeds, right? But you can look up the speed of sound. You can literally just talk about, the speed of sound is 340 meters per second. Why can we do that? We can do that because sound is not a thing. It's a freaking wave pulse. And when we say the speed of sound, what we really mean is the speed of sound traveling through air at standard temperature and pressure. Like if sound could also travel through water, totally fine. And if it travels through water, it will also travel at a constant speed. It'll just be a different constant speed from the air one. So what I'm saying is the medium fully fixes the speed of information propagation. But once you know the medium, you know the speed at which information is going to propagate. That's why we like sending information through media in the form of waves. Like this is what's crazy about waves. Furthermore, or finally on this whole thing, and then I'll pause. When I say number two, okay. Again, I have to be very careful. I could go on this forever. This ties back. You'll see why this is so important. I hope one way or another, we're going to tie electricity and magnetism back to this. And ultimately, what I'm trying to do here is drill points into your head that have to do with how sound waves work. The more you can picture how sound waves work. So I'm not trying to play hide the ball. The better you can understand how sound waves work, that lays the foundation for ultimately understanding how electricity and magnetism come together to make light waves, which is really the punchline of this course. Okay, I mean, the punchline of this course, or the end of this material, one way or another, is how electric fields and magnetic fields come together to make light waves. Now, we're gonna have to rush. I'm always rushing. It's a 5-week course, yada, yada. There's so many beautiful things to say. I won't be able to say all of it, or, you know, to talk about, but so that you can just see the arc of the course, or you can understand why I'm asking you to care about certain things that I'm asking you to care about, is ultimately electric fields and magnetic fields are going to come together in life and make something called a light wave. And that's a fabulous thing. The light wave, there's ways in a light wave is a fabulous thing. It's like its own thing, but it's in part a wave. The best way to understand why a light wave is such a particularly interesting form of wave is to first understand what waves are in the first place. The best example to hold in your mind is either just that thing, just a, you know, a pulse that's going along a string. That's the simplest form of a wave. Whenever you're trying to understand waves, try to bring your head back to that, to lab 3, because everything that we ever say about waves is going on in that distilled pure example of just a hump traveling along a string. But if you think you sort of get that, if you get the points I'm making about that, it might be helpful to extend that to thinking about sound. Sound is that, just it's in 3-dimensional space rather than 1-dimensional space. And it's, you know, through a gas rather than through a solid. So like there's details that are different, but the math is essentially the same and the concepts are the same. One thing I'm trying to tell you now then is when you picture sound going from like my mouth to your ears, I want you to understand that it is a pulse, it's a wiggle, it's a propagation, it's a disturbance of the arrangement of air molecules. And that disturbance, so it's not a thing, but it's a disturbance. It's a bit of information, I would say. Like that disturbance is happening at a certain rate, and that rate is a number. That number is a piece of information. That's what's traveling from me to you when I send a sound wave or other kind of wave to you. And the thing I want you to picture now, hopefully you can see in the math, but even if you don't see in the math, what I want you to picture is like whenever we send a wave pulse from one source to a receiver, it will travel at a speed that is constant and entirely determined by, entirely fixed by the medium through which it travels, which means now, and this is where your whole board meeting came into play and stuff like that, if the medium determines the speed at which something travels, that means it travels at that speed relative to the medium. Like this then all brings us back to Galileo and physics 1 and the relational character of speed. Like remember, speed and velocity from the get-go, speed or velocity, whichever one you want to say, from the get-go is a relation, right? I don't have a speed in the universe. I have a speed relative to the floor or relative to the surface of Earth, or me and Earth together have a speed relative to the sun. Like nothing has a speed by itself. Everything is moving at a certain rate compared to something else. And if I'm on a subway right now and I ask, like, how fast am I going? You could rightly say to me, what do you mean how fast you're going? I mean, how fast are you going like compared to your seat? Because the answer is 0. You're just sitting in your seat. You're like not doing anything. That's why you're not sweating. But if you're asking how fast is your seat going relative to the platform or relative to like the New York City streets, well, then the answer is 100 miles an hour. Oh, but I guess the New York City streets are like cemented to planet Earth. And if you're asking how fast they're going relative to planet Earth, then it's like 100 miles an hour. But of course, all of planet Earth is going at like 65,000 miles an hour relative to the, right? And all those questions, like you don't want to get a headache or anything, but they're just a reminder that speed is a comparison, always. You can't have speed of one object. It always has to be the speed of an object compared to something else. And what you choose as your basis of comparison will affect what number answer you get. And all answers are right, depending on, I mean, there's more than one right answer, depending on what you're comparing things to. So when we say that sound travels at a certain speed through air that is fixed by the air, like, and I totally am saying that, I'm going further and saying, well, really what I mean is sound will go at a certain speed compared to the air. Like sound will travel through the air at a certain speed because or just like the ripple on the string will go through the string at a certain speed compared to that string. The fact that the string is on the earth while all this is happening is not going to, like, we don't have to take that into account necessarily in the speed, right? It's compared to the medium. So the medium plays this crucial role in the propagation of a wave pulse. And what that ends up meaning is, if anybody ever moves relative to the medium, or the medium moves relative to a source or a receiver, then funkadelic things happen. This is the Doppler effect. I know you already did the lab. It's kind of like, in a way, too late for me to prep you for it, but maybe this will clarify the whole discussion you were just having yesterday in the board meeting, because all about the fact that sound necessarily goes at a fixed speed relative to the air. It does, 340 meters per second relative to air. But if the thing making the sound moves through the air, or the thing receiving the sound moves through the air, well, sound is definitely going at that speed relative to the air. But then the air is going at a certain speed relative to either a source or a receiver. So next thing, so suddenly we're going to have somebody observing, and this is totally true, or just picture if there was wind, if you sent sound, which is all the same thing. If you sent sound through air, but the air was moving itself toward you, like if you had wind, then now the sound is coming toward you faster than it was actually sent. And that ultimately means you're going to observe or receive or measure a different frequency from what was sent. Just like if I stand at Coney Island and wave fronts are coming at me at a speed of 2 meters per second, in other words, like 6 meters between every wave and whatever, if wave speeds are coming in at me at 2 meters per second, and if there's a frequency of like 3 of them every second or whatever, that's all well and good. But if I start running into the waves, for sure, they're going to hit me more frequently, right? Because what they're doing is relative to the water, period. If I do something relative to the water, or the water does something relative to me, then that changes the game for me, not for the water, for me, not for the boat that made the waves, for me. That's the nature of the Doppler effect. In other words, long story short, because all waves travel at, well, short story long, because all waves travel at a speed that is fixed by their medium and constant relative to the medium, on the one hand, waves have this totally reliable character of motion. Like they're like all the fun of physics with never having to deal with acceleration, which, by the way, like would mean you would, if everything in life were a wave, you would not even have to deal with half the material from physics 1. Acceleration is like the big pain in our butt. Waves don't do it. They all travel at a constant speed. By the way, so constant. This is a game I always play with my sons at the beach. It's not a game. It's like they don't think it's fun. But like, this is how true what I'm saying is. All of you have seen ripples a million times in your life. Like you've seen ripples at the beach or in a pond, or you drop a rock in a pond and the ripples spread out, or just in the bathtub, you just go like, darn, 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 like with a rubber duck or whatever, and there's ripples, right? Picture any situation of waves that you ever picture that you're pretty confident are waves. Now, here's something. Ask yourself, when's the last time you saw one ripple catching up to another? Or when's the last time you saw a ripple catching up to another and passing it? I'd wager the answer is never, because it never happens. Like you can have 2 ripples coming from opposite directions and cross. That's called interference, but you'll never see one ripple catching up to another ripple ever. And whatever space is between, whenever you draw waves on a piece of paper, you just automatically all sort of draw them like all evenly spaced from each other. And like, you don't even think about it, because they are. Because wave ripples never catch up to one another, because they don't go faster or slower than one another. They all go the same freaking speed reliably. So once you see a space between the ripples, it just continues as that space. And we call it the wavelength. Like they're so reliable, you don't even think about how reliable they are. Wave ripple. I've said to my son before, when he was like 4 years old and he was bothering me, I was like, go stand over there and tell me the minute you see a wave ripple catch up to another one. It was like obnoxious that I did that, because like you won't ever see that. But yet you don't think about it. You're just like, oh, waves, because they're just like so reliable. You don't even marvel. Now, I don't know what you do. I didn't even marvel at their reliability until this all sank in my brain. That waves travel at a speed that is fixed by their medium, which on the one hand means it's incredibly fixed, it's incredibly constant, it's incredibly reliable. On the other hand, and I'm talking real world, not just the math. On the other hand, all you got to do is move the medium, and now you've had a severe impact, or move relative to the medium, and now you've had a severe impact on the waves. Like you can literally make waves catch up. Like, oh my God, I really have to stop. But like this is why you can do the whole Doppler effect thing, why we make you have a whole debate about it and everything. We really want you to see what a huge role the medium plays in the propagation of waves. It makes such a difference. You can end up playing these weird games with waves that you can't play with particles. I mean, so last quick example, if this is making any sense to you, and if it's not, I apologize, and I'll go on and make a different kind of not sense to you with the 30 minutes that we have left. But like, I mean, like, look at this. If you're standing on a train and you throw a baseball off the train, like you throw it as fast as you can throw it. Say you could throw a 75-mile-an-hour pitch. So you're standing on a train, you throw a baseball off a train. It's a 75-mile-an-hour pitch relative to you, right? Like, I'm just making up a number, but there's like a reasonable number. So that means the baseball goes away from you at 75 miles an hour. Fine. That means like if it were a really long tunnel or like really had no place to fall, like an hour later, it would be 75 miles ahead of you. I mean, obviously that's ridiculous, but that's what that number means. Fine. But say you're staying on this train while you do that. So now you let the train go 100 miles an hour through the tunnel while you're throwing your baseball. That's kind of interesting. If you were to do that, I hope you can sort of picture or understand that if you're standing on a train while you throw a 75-mile-an-hour pitch, and if the train is going 100 miles an hour past the people on the platforms, okay, on the one hand then, that definitely does mean that your baseball is traveling at 175 miles per hour relative to the people on the platform, right? I don't mean that as a surprise. I just want to establish it or remind you, right? Like velocities work that way. Velocities are relative. If the baseball is going 75 miles an hour to you and you're going 100 miles an hour relative to the platform, then the baseball is going 175 miles an hour relative to the platform because the baseball is just doing what it's doing relative to its source, right? I hope that makes sense so far. In other words, put one other way, the baseball is always ahead of you. The baseball is always going 75 miles an hour faster than you. Even if the train is going 100, that just pushes the whole phenomenon forward by 100. You're not going to put another way, I'm saying, I don't care how fast that train is going. You're not going to catch up to your own baseball, right? Like you're going to throw it at whatever speed you throw it, and it's going to go that speed relative to you, no matter what that speed is. And if you're going super fast while this is happening, then the entire situation will go that fast past the platform people. That's what particles do. You cannot catch up to a particle that you just threw. That would make no sense, right? I mean, it's like, unless you started moving after you threw it. But if you throw sound off the top of the train, let's just get it straight. I mean, if you shout off the top of the train, now the sound will travel out your mouth at 340 meters per second, not relative to you, but relative to the air that you're in. Like, this is the difference. Waves travel at a speed that is fixed not by their source, but by their medium. So if you're on top of a train or a plane and you shout or you make a noise, the sound now goes out your mouth at 340 meters per second relative to the air, regardless of what you're doing. It will go 340 meters per second relative to the air. So if you are traveling at 240 meters per second when you do that, it's not going to travel 340 relative to you. It's only going to be 100 ahead of you. Put more exaggeratedly, like if you made sound while you were traveling at the speed of sound, the sound would not get ahead of you. It would just pile up next to you because it's traveling at, if you traveled at 340 meters per second through the air while you sent sound out, the sound would go at 340 meters per second relative to the air. So it would just pile up next to you. Like literally, it wouldn't get ahead of you. It would be going the same speed of you. You would catch up to it, unlike a baseball. And if you now went faster than it, then you would crash through this entire collection of oscillations, this wall of sound that was just going through. Like you could beat your own sound, and if you could go faster than the sound goes in the medium. You cannot do that with a baseball. You can't throw a baseball and go faster than it, but you can throw a sound out. You can't throw a baseball and then like run and catch up to it, but you can make a sound and catch up to it and then pass it. And that's called a sonic boom. That's literally what a sonic boom is and actually the more limited version of it is it's called a wake. if an object making a wave actually goes faster, then the speed at which that wave goes relative to the medium, then first of all, we experience that as a wake, like when motorboats go faster than or ducks move fast, are making waves in the water, but they're going faster than the waves actually go in that water. They can do that. You can't do that with a baseball, but you can do that with a water wave because the water wave has to go at a certain speed that's fixed by the water. So if a duck goes faster than the waves that it's making, and by the way, it can't control how fast it's making those waves. So if it makes waves at all, and then goes faster than that speed, then they arrange themselves in this weird thing called a wake behind it. And if sound is involved, if it's an airplane going faster than the speed of sound in air, then we have this huge boom. Or if you take a long towel and you wrap it up and you like dip the end in water, or in other words, you make a whip, right? You make like out of leather, you make a whip and you crack the whip. What you're doing then is you're making this thing go really fast. You're making the end of a whip of a piece of leather or like a towel. When you go like this, the end of the whip moves through space at a speed that's faster, because it's like so small, it's easy to do. It moves at a speed that's faster than the rate at which sound travels through it. Like this is what a whip is, or the crack of a whip. It is that end point where the little point now moves through the air for a moment faster than the very waves that it made can move through it. So it overtakes its own collection of sound and crashes through it. And that you hear is a mini sonic boom. Like these are crazy things that we can do. I mean, I don't know if you think that's crazy or not. I think it's crazy. Like you can do that kind of thing with waves. And that's what the Doppler effect is all about. It's all about the fact that waves go at a speed that is fixed and constant, determined by their medium, but by their medium, which means all we got to do is move the medium or move past the medium. And now we're doing funky things compared to the waves. That's the point of that. Caleb totally has his hand up, and I totally do see. We're going to get Caleb, and then I'm going to take a breath and go. And I'm sorry, but that's why we care about that. That's a major difference between wave motion and particle motion. So if I got hit by a truck right now, we did nothing more with the material. I want you all to know that if you ever hear about light, or like light going a certain speed, or light being electromagnetic waves, what people are trying to ultimately say is that light is a very special version of that. Okay, Caleb, sorry, go.
So wait, so what is it that causes, like, why does it cause a loud noise when a sonic boom happens? What's happening that the wave?
Okay, what's happening is like you collect by, what's happening is that by going the same speed as the sound, you, the object, the source of the sound, by going fast enough, it stays with the sound. Like, let me back up for a second and say what sound is in the first place, right? Is like little vibrations of air molecules. But, and maybe this, I don't know if this helps or not, but it happens to be the case with air molecules when they vibrate, like, or oscillate, instead of air molecules between you and me, it's not like the one at my mouth goes up and then down, and then the one next to it goes up and then down. Like that's what happens on a string. But with air molecules, what actually happens is the air molecule near my mouth goes forward and then back. And the air molecule next to it then goes forward and then back, and then forward and back. So the air molecules are actually like pushing against each other, like in a line. So we call this a compression. It's a compression wave. They're making little areas of high compression air molecules. And then so like close to my mouth at one moment, there's like all these air molecules packed together really closely. And then next to it, they're spread apart. And then next to that, they're really close. And then next to that, they're spread apart. So in other words, like the crest of a sound wave really means, the crest of a sound wave really means a high pressure zone of air molecules, like all packed together. And then a trough would be like the air molecules spread apart. So here's the point then. When I'm making sound, I'm making like compression packet, uncompression packet, compression packet. I'm making all these little packets, these high density packets of air molecules. If I move at the same speed that they're traveling out from me, then I stay with them, right? Because they're doing this at a speed that is like relative to the air. Like they're doing it at a speed that doesn't care about me at all. So they're doing this they're getting to you, these packets, these compression packets are pulsing to you at 340 meters per second. If I'm in an airplane and also travel at 340 meters per second, that means I'm going to like literally stay alongside a bunch of these packets Like they won't escape from me. They'll be right next to me. So I'll be in this zone of all this air that's all packed together. Yeah, like, so this big sort of, so I'll be like a bunch of crests will just collect on top of one another because even though they're all going, I'm all going too while I make them. So I keep making a new crest and just putting it on this pile. Like I make a new crest, a new compression packet, and it should escape out from me, but then I run and stay with it. So I'm just piling all, so it would be like, well, I don't know what it'd be like, but so I'm building up this big pile of compression packets that otherwise normally would escape and form out into a line. But since I keep running forward every time I make one, they are all gathered and they'll all stay with me. And if I now go even faster than that and accelerate forward, I literally crash through, I literally drive through or move through a huge high pressure zone of all of these packed together air molecules. So if sound in the first place, if when you hear sound, you're hearing little crests, like to hear sound at all, for it to have any volume is to have a bunch of crests that reach your ear. Well, I've got all these crests here. They're all collected. It's like constructive interference of an enormous number of sound crests. So it's this big wall of sound that the minute I go through it, I hear all at once, and that's the boom. I mean, that's a, does that make,
Yeah, so real quick, just to clarify one thing, can I show a picture of a diagram to ask you about this?
yes, please. And that's points, by the way. So submit it later, but yes, go for it, please.
Okay. So basically, you're saying like this is the see if this is the jet. Once it gets to this like triangle, once it gets to this point, it's up against all of the sound waves that's created, and they're probably getting back and forth. And then you're saying at that point, if it moves past, it's sending its waves through that, and that's what's it's sending like more sound waves or energy waves through the previous overlapping waves, and that breaks it, and that releases some sort of energy that comes out in the form of what we see as a sonic boom.
Yes. That's
Got
cool.
it. Okay.
That's cool. Right. That's awesome. Okay. So that's awesome. Totally. And yes, he should submit that for, and there's still a week for other people to do this too, but he just showed a, what do you call it? Screen share. There's definitely a portal for that somewhere in that, but yes, no. And of course it's not all about points, but yes, no, totally awesome. Okay. Let me just pause for a second. Let me just breathe for a second. Okay, that's a lot. Again, the takeaway of that is wave motion is different from particle motion. One way to know that wave motion is that it's got a speed that's fixed by the medium. Okay, so you know what the takeaway of all that to everybody? I'm going to I know we only have 15 minutes now, and that's fine. That's on me. I'll adjust, blah, blah, blah. But I am going to use these 15 minutes. I know this has been dense in its own way. I'm going to use these 15 minutes. Am I right? Yeah, these 15 minutes. And the segue or the connection of all this is this shows the importance of a medium. Okay, I'm saying that the medium for a wave is the carrier. Think of a wave pulse as raw information. When a wave pulse travels, a thing does not travel. Raw information travels, such as the number 256 hertz. When a wave travels, raw information travels. The thing through which it travels is the medium. Okay, I'm going to write this actually. So here's the segue.
Professor, where do we put through at? After irritating?
Oh, sorry, really good question. Sorry, really good question. No, after blockade. Thank you. I'll rewrite it. Really good point. I'm glad you paid such attention. After blockade. It's a weird sentence. I'll read it out loud, but good point. Wait, hold on. Hold on. You guys really do pay attention. Okay. And I'll read this out loud in one moment. Okay. So takeaway of everything I'm saying, I mean, I honestly think there's a lot of takeaways, but like the big conceptual takeaway, or at least, and the thing that will link us back to electricity and gravity and all that, is I'm saying the medium for a wave pulse is not just an incidental or irritating blockade through which the pulse must struggle. Rather, the medium is vital for the transmission of information. What I'm trying to say here, or maybe I should read it again, right? Hopefully. Right. So the medium for a wave pulse is not just an incidental or irritating blockade through which the pulse must struggle. Rather, the medium is vital for the transmission of information. And vital is a big word. Vital means like would not be alive without it. Like vital means like alive, right? And so what I'm saying sort of quickly here is like when we say that sound travels through air, when we say the speed of sound is 340 meters per second, like in air, or when we say sound can also travel through water, and it could travel through a whip, through leather, and it could travel through air. I just want to make it clear to everybody, because I used to have this misconception. When I heard of sound traveling through air, I always thought it was like there was sound, right? And like sound is traveling along, but then there happens to be this like air everywhere. So the sound, so I always thought of the air as like this annoying, like interfering, like I knew it was called the medium, but I thought air was the thing that was in the way of the sound. So when they talked about the speed of sound going through air as being a certain number, I always sort of imagined in my mind without realizing it, that it was like, oh, if only the air weren't there, the sound could get through much faster. I thought like the sound has to like make its way through the air, and the air is like in the way. And I thought of it as kind of like swimming through the water, where like, oh God, like the water's so thick and I have to use my muscles so much to get through this water. Well, there's some truth in that analogy, but the thing I fundamentally that's wrong about that, that's really important, like not to think that way, is that no. There wouldn't be sound unless there was the air, or unless we had something else like water. Like you may have heard this, and it's true. Like there is no sound traveling in outer space. There isn't. Like literally not. Like because there's nothing to carry the sound waves. Sound is a ripple in a bunch of things that are usually air molecules. But if we don't have air molecules, we use something else like water molecules. But you need a bunch of things to vibrate back and forth in order to send this pulse. And you need them so crucially that the precise nature of those things that's vibrating back and forth will determine exactly the rate at which the pulse will propagate. Or in other words, it will determine the rate at which the raw information will travel. So it's really important to realize the medium is not just in the way. The medium is the carrier. The medium is the vital piece that not only allows the whole phenomenon to happen, but actually determines the details of the phenomenon. The medium is crucial to the transmission of information. If you want to send raw information from one place to another, which is what we're talking about here, we're not sending things, we're sending numbers or ideas or whatever. If you want to send raw information from one place to another, according to all this analysis, A, you need a medium to do it. B, the precise nature of the medium will determine the precise rates at which it occurs. I'm going to call on Caleb. I'm going to caution. I definitely have to somehow get something out before 3:55. I'm making it shorter and shorter as I go, but I'm getting a little nervous about time. It's my fault, but Caleb, go. I might be fast with you. That was what I'm saying, Caleb, but go.
Got it. So then is everything like, is every type of individual wave simply the results of its medium? Like, for example, is there just one, is every longitudinal or transversal wave, just energy in transversal or longitudinal form, and depending on the medium, it's either sound or light or whatever.
Perfect. Exactly. I could not say it any better. Honestly, that's totally worth, that was worth saying. That's totally right. If anybody just got anything out of what he just said, it's right. It is my point. It makes me feel like I am making a point. It's totally right. And it's worth saying because, like, yes, for example, if you've ever heard of seismic waves or like earthquake, like earthquakes, like seismic waves, like stuff going through the earth, those are compression waves of earth. What Caleb just said is exactly right, meaning that they are just sound waves, but in a medium of ground rather than a medium of air. I can't put it any better than what he said, but yeah, there's just waves, and what makes one wave different from another is the medium through which it's going, especially once you distinguish between longitudinal and transverse. It's totally right. Wait, so is your hand still up, or is that just like a, or can you?
No, yeah, that
Okay.
was just from before, but actually just one more thing. So yeah, I added the transversal and longitudinal because I thought, all right, sound and light both seem like they travel in air, but light is transversal and sound is longitudinal, correct? That's why they're both.
That is correct. That is correct. Yeah. Okay.
Okay.
Okay. Cool. And now to everybody, just, yeah, that's correct. And again, if I got hit by a truck right now or whatever, like the punchline of all of this is light. Like where this is all meant to be going is light. Light is the prize at the end. Right, so I have to caution anybody. I keep alluding to light as like a foreshadow, no pun intended, because it's the prize at the end of the package. But I do want to caution everybody, it's a prize because it's based on all of these understandings, but then it ends up doing its own thing. Like some of the understandings that I'm laying down here seem to get violated by light, but it's just like playing jazz piano or whatever. Like we have to lay down the scales and understand them before we start breaking them and understanding what's being broken. So I don't want to lie to anybody. Like some of the things that turns out with light, like seem to go against some of what I'm saying, but they don't, you wouldn't even know that they're going against unless you knew these things first. So, but yes, that statement he just made was true. Yes. Okay. Now it's 3:48. I really have to think about this. Okay. Okay. I'm just going to do this. I'm going to do a lot less than I would. I'm not going to crowd 14,000 pages now in the next 7 minutes. Like we all are human, but I do have to at least put on the table how this brings us back to electricity, because that is the point. Oh, sorry. Okay. I only have 4 minutes to say this, so I'm going to say it. We said that for any point charge in the world, proton, electron, whatever, it automatically oh, and I should say, I'm sorry, plus or minus. Any all right, I'm just going to leave it like that. Right? For any point charge in the world, it automatically pulls or pushes on any and every other point charge in the world with a force dictated by this equation, by these magnitudes arranged this way. And in this vector way, we dealt with the vectors yesterday. I have to go back to the vector stuff and all of that, and that's in the, but I'm not going to worry about that right now. I'm just saying that we made a claim that every charge pulls on every other charge through empty space automatically. In the same way that every star in the universe apparently pulls on every planet, for example, through empty space. What I'm going to say, I got to think how to say this in 3 minutes. Hold on a second. Okay. Of course, we're going to get back to this on Monday, and I am watching the clock. I'm not going to keep you over, but we're going to switch from here on in for our attention from forces to fields. A force is an interaction between two objects. A proton exerts a force and pulls on an electron, or a proton exerts a force and pushes on another proton. The sun gravitationally pulls on the earth. So there's two objects involved in every force, and there's two objects involved in every one of those force equations. Either it's Q1 and Q2, or it's M1 and M2. From here on in, instead of saying that the proton pulls on electrons, we're going to say that the proton creates a field of a certain strength at every single point in space around it. And that if you were to put an electron anywhere in that field, then the field exerts a force on the electron, and the electron gets pulled. Or put another way, I'm saying we're going to introduce, in effect, a medium between all two objects that experience action at a distance. Instead of saying the sun pulls on the earth directly, we're going to say from here on in that the sun creates a field between the sun and the earth at every point in space, and the field pulls on the earth. Mathematically, what we're going to say is super simple. We're literally just dividing out one of the two objects in our original equation. We're saying from here on in the electric field generated by one object is simply the electric force divided by the magnitude of charge of the second object. The electric field created by a proton is the amount of force that it would exert at any given location if a 1 unit positive charge were located at that equation. At that location. Or put it another way, and I'm still not watching the clock, we're saying the field from now on is how many newtons of force something exerts per every 1 coulomb of positive charge, of test charge, that could be located at that location. Field is between two objects. Field is something, force is something that I exert on you. Field is something that I exert on space. And then if you happen to be at that space, you experience. Force is between two objects. Field is between one object in space. And the only mathematical difference is that a field is force per unit of charge. Force is measured in newtons. Field is measured in newtons per coulomb. Mathematically, it's that simple. We're just about to end right now. But from now on, we're saying that we believe that there's a field, that the sun doesn't just pull on the earth in empty space. The sun creates a field in empty space, and then the field exerts a force on earth. If you think that's weird, you should. It is weird. We're going to talk more Monday about why we even believe in this notion. It's kind of like we're saying from now on, all forces that happen at a distance all forces must have a medium to convey the information of that force. That medium is the field. I mean, that's the time between all this. I know it's now 3:56, but what I'm really saying is if you think that the idea of a field is weird, you're right. But don't think of it as something that poses, don't think of it as a weird thing. Think of it as an attempt to answer the even weirder question of how the heck could the sun pull on the earth if there was literally nothing between them? How could the sun send the information of itself to the earth if there was nothing in between? I'm going 1 minute, I'm going to go one more minute over time, and then I'm going to say you can leave. Let me put it really one really specific way. If you believe that gravity, like created by the sun on the earth, is based on how far away the earth is from the sun. Like if you believe in the r squared in the denominator, then just ask yourself this. If the sun pulls the earth and now the earth gets closer to the sun, then doesn't the sun now have to pull with a stronger force? And if so, how did the sun find out that the earth is now closer to it? How does the information of the earth's location freaking get to the sun at all unless there's some kind of medium in between carrying that information at some rate, at some speed? If the information of the earth's whereabouts can get to the sun at all, or if the information of an electron's whereabouts can get to a proton at all, ask yourself, does it take time for that information to go, or does it just get there instantaneously? I think you'll find that the answer either way, it's freaking weird. If the proton knows where the electron is, which it must if the force exerted, it not knows like consciously, but if the proton has the information of the electron's whereabouts and those informations determine how strongly the proton pulls, then that information must be continuously updated to the proton. How is it getting there? What is containing the information? What is transmitting the information? We call that a field. I went 2 minutes over time, 3 minutes over. I totally apologize. I'm totally done. I will see you all. You've been very patient. I will post the video, blah, 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 blah. You don't have any new homework. Just work on fine. Thank you very much. Yes, have a good week. Thank you. Weekend.
Thank you so much, Professor.
Thank
Have
you.
a great weekend.
You have a great weekend. Thank you very much. Seriously. Okay, I'm looking at you. Thank you. Oh, thank you.
Oh, Professor, just as a reminder, when is the test again?
Wait, the final?
Yeah.
The final will be posted Wednesday evening, somewhere between 4 and 7 p.m. And then it'll be due back to me by Saturday noon. So it'll be posted a week from today, and then it'll be due back. Thank you very much. And then it'll be due back Saturday, the 21st by noon.
Got it. All right. Thank you. Super fun.
Yes. Yeah. Wait. Right. Okay. Hold on. Yeah. Wait. Hang on for a sec. Wait. Okay, well, 1 second. Oh, you are the okay, he's up here. You're the only one here. Okay. Yes. No, we totally oh yeah,
I
okay,
know,
no.
but that's all we can do. That's like all the school can give you. Then I don't think I have a choice for that. In that case, you know, that's gonna be
Well,
very.
no. But wait, but I thought you. Well, hang on. Two things, because I really meant everything I said. I want to help you, and you totally asked me before all this. So no, we still want to help you. So there's two options. One, I mean, your original option was like doing something early, which you still could do. I think it's gonna be very hard on you, but we can still do something early with you. But the other thing is, wait a second. Well, tell me this. Wait, you tell me, because I still respect your circumstances and that you told me about them. So if I didn't say anything today, if we didn't have a school rule, like if you could design the plan, what would the plan? And I'm not being sarcastic. If you could just design the plan,
How many questions is the exams? That depends. I like to do the exam day by day. I want to do it only one sitting.
okay, it's probably going to be 2 long problems and 1 short problem, I think. Not long, but I mean, like, I want to make it shorter than the midterm. So the midterm was like technically.
No, I asked my parents again. I'm literally what's it called? Thursday night. I made a mistake. It's Thursday night. That's the absolute last thing I'm gonna be here. And that's to be inconvenience. In the last 2 days, I'm gonna be busy, so I'm not gonna be able to do the exam.
Okay, wait. Wait. Thursday night. What if
I was like, could you post it like Tuesday, and I'd be able to finish it by Thursday, and I could be done with it.
Well, what if we say that I can definitely, if you don't mind, I could definitely give it to you Tuesday.
I go. That's perfect. Tuesday and after class, I guess, like signing. I could finish it by Thursday afternoon.
Yes, I think so. With just two things. Just one. First of all, please remind me Monday so I can make sure. But also, is this okay with you? Just because these I'm happy to do that, and I could even give it to you earlier. But I just want to warn you: are you okay with what I give you? Might not be the exact same thing that I give everybody else. In fact, yours might be even shorter or something. I'm going to cater yours a little bit to you, not to make your life harder, but I'm going to make yours a little different so that you can be ready to take it up by that time. But also that I don't want to give anybody the false impression, even if you can work with other people and stuff and they can look at yours, but they shouldn't assume that theirs will be exactly the same as yours when they get theirs Wednesday. I mean, if you're okay with that, I'm okay with that. Is that?
All right. I'll work with that.
For me, okay. All right. And I promise you, I won't make yours harder or something. Honestly, in fact, I'm going to just try to make sure that yours doesn't have like material on it that we didn't already cover or something like that. So, but yeah, I can give it to you by Tuesday. Just remind me Monday is the only thing.
Sure. And also, you left the recording on when talking about this.
Oh, crap. You're right. All right.